Did you know that while you sleep, the universe is still uncovering its deepest secrets? Let's explore some of the most fascinating mysteries of the cosmos together. So, sit back, relax, and let the universe guide you into a peaceful sleep as we dive into these incredible facts. The universe, in all its vastness and complexity, remains a profound mystery to humanity. One of the most perplexing and elusive aspects of the cosmos is dark matter, an unseen force that permeates the universe and shapes its very structure. Despite being invisible to our eyes and undetectable by conventional means, dark matter is believed to constitute approximately 27% of the universe's total mass and energy. This enigmatic substance plays a crucial role in the formation and evolution of galaxies, yet we know astonishingly little about its true nature. In this exploration, we delve into the evidence supporting the existence of dark matter, the methods scientists use to infer its presence, the theoretical frameworks that seek to explain it, and the implications this mysterious component of the universe holds for our understanding of cosmology. The concept of dark matter first emerged in the 1930s when Swiss astronomer Fritz Zwicky observed the Coma Cluster, a collection of galaxies bound together by gravity. Zwicky noticed that the visible mass of the galaxies within the cluster was insufficient to account for the observed gravitational effects, such as the speed at which the galaxies were moving relative to one another. He hypothesized the existence of a missing mass, an unseen substance that exerted gravitational forces strong enough to hold the cluster together. This was one of the earliest indications that there was more to the universe than what could be observed through telescopes. In the decades that followed, further evidence for dark matter accumulated. One of the most compelling pieces of evidence came from the study of galactic rotation curves. In a galaxy, stars orbit around the galactic center, and the speed at which they move should decrease with distance from the center, similar to how planets in our solar system move slower the farther they are from the sun. However, observations of numerous galaxies revealed that stars at the outer edges were moving just as fast as those closer to the center, a phenomenon that defied the expected decrease in velocity. This discrepancy suggested that there must be an additional, unseen mass contributing to the gravitational pull, leading to the conclusion that galaxies are enveloped in massive halos of dark matter. While the gravitational effects of dark matter are evident, detecting it directly has proven to be an immense challenge. Unlike ordinary matter, dark matter does not emit, absorb, or reflect any form of electromagnetic radiation, making it invisible to telescopes that rely on light, radio waves, or X-rays. This has led scientists to employ indirect methods to study dark matter, focusing on its gravitational interactions with visible matter. One such method is gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity, where the gravity of a massive object, such as a galaxy cluster, bends the path of light from a more distant object behind it. The degree of bending allows scientists to estimate the total mass of the lensing object, including any dark matter present. Observations have shown that the mass inferred from gravitational lensing often far exceeds the visible mass, providing further support for the existence of dark matter. In addition to observational evidence, theoretical models have been developed to explain the properties and behavior of dark matter. The most widely accepted model is the cold dark matter (CDM) paradigm, which posits that dark matter consists of particles that move relatively slowly compared to the speed of light. These particles interact weakly with ordinary matter, meaning they rarely collide or scatter, allowing them to clump together under the influence of gravity and form the scaffolding upon which galaxies and large-scale structures of the universe are built. The CDM model successfully explains the distribution of galaxies in the universe and the formation of cosmic structures over billions of years, making it a cornerstone of modern cosmology. Despite the success of the CDM model, the nature of dark matter particles remains unknown. Several candidates have been proposed, including weakly interacting massive particles, WIMPs, and axions, both of which have been the focus of intense experimental searches. WIMPs, for example, are hypothetical particles that interact via the weak nuclear force, making them difficult to detect but potentially observable through rare interactions with ordinary matter. Experiments such as the Large Underground Xenon LUX detector and the Cryogenic Dark Matter Search CDMS have been designed to capture these elusive interactions, yet so far no definitive detection has been made. The search for dark matter has also extended into the realm of particle physics, particularly with the use of particle accelerators like the Large Hadron Collider LHC at CERN. By smashing particles together at incredibly high energies, physicists hope to produce dark matter particles or observe evidence of new physics that could shed light on its nature. While the discovery of the Higgs boson in 2012 was a monumental achievement, providing crucial insights into the mechanism of mass generation in the universe, the LHC has yet to uncover direct evidence of dark matter particles. This ongoing search highlights the challenge and the potential for breakthroughs in our understanding of the fundamental building blocks of the universe. As researchers continue to probe the mysteries of dark matter, alternative theories have also been proposed to explain the gravitational phenomena attributed to it. One such theory is modified Newtonian dynamics, MOND, which suggests that the laws of gravity may need to be adjusted at extremely low accelerations, such as those found at the outskirts of galaxies. While MOND has had some success in explaining galactic rotation curves without invoking dark matter, it struggles to account for the full range of observations, particularly on larger scales, such as galaxy clusters and the cosmic microwave background. Nevertheless, MOND and similar theories serve as important reminders that our understanding of gravity and the universe as a whole may still be incomplete. The study of dark matter is not just an academic pursuit. It has profound implications for our understanding of the cosmos and our place within it. Dark matter is essential for explaining how galaxies form and evolve, and its gravitational influence has shaped the universe from its earliest moments after the Big Bang. Understanding dark matter could unlock new insights into the fundamental forces of nature and the origins of the universe itself. Moreover, the technologies developed in the search for dark matter, from advanced detectors to powerful computational models, have the potential to drive innovation in other fields, including materials science, engineering, and information technology. Despite the progress made over the past century, the mystery of dark matter remains unsolved, and many questions are left unanswered. What exactly is dark matter made of? Why does it not interact with light or other forms of electromagnetic radiation? How does it fit into the broader framework of physics? And what does it tell us about the ultimate fate of the universe? These questions drive ongoing research and inspire new generations of scientists to explore the unknown. As we continue to investigate the dark matter that holds our universe together, we are reminded of the limits of our knowledge and the vastness of what we have yet to discover. The pursuit of dark matter is a testament to the human spirit of inquiry and the desire to uncover the hidden truths of the cosmos. It is a journey that will likely continue for many years, if not decades, as we strive to piece together the puzzle of the universe's invisible majority. Looking ahead, the search for dark matter will likely intersect with other cutting-edge areas of research, such as dark energy, the mysterious force driving the accelerated expansion of the universe. Understanding dark matter and dark energy together could lead to a more comprehensive picture of the universe's composition and its ultimate destiny. As we transition from the study of dark matter to the exploration of dark energy, we find ourselves on the cusp of a new chapter in our quest to understand the cosmos, one that promises to be as challenging and rewarding as any that has come before. The universe is vast, mysterious, and governed by forces that we are only beginning to understand. Among the most perplexing of these forces is dark energy, a mysterious entity that makes up approximately 68% of the universe's total mass energy content. Despite its overwhelming presence, dark energy remains one of the greatest enigmas in cosmology, driving the accelerated expansion of the universe in a way that defies our conventional understanding of physics. This expansion, first discovered in the late 20th century, has profound implications for the fate of the universe, the nature of space and time, and the fundamental forces that govern the cosmos. The concept of dark energy emerged from observations made in the late 1990s by two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team. These teams were studying Type Ia supernovae, exploding stars that serve as standard candles because of their consistent intrinsic brightness. By measuring the redshift of these supernovae, which indicates how much their light has been stretched as the universe expands, astronomers can determine their distance and, by extension, the rate of expansion of the universe at different points in time. To their surprise, the data revealed that distant supernovae were dimmer than expected, suggesting that the universe's expansion was not slowing down, as previously assumed, but was instead accelerating. This unexpected finding led to the postulation of a previously unknown form of energy, dark energy, that permeates all of space and exerts a repulsive force, counteracting the attractive force of gravity. To understand how dark energy drives the expansion of the universe, it is essential to delve into the principles of general relativity, the theory formulated by Albert Einstein in 1915. General relativity describes gravity not as a force in the traditional sense, but as the curvature of space-time caused by the presence of mass and energy. Massive objects, such as stars and galaxies, cause space-time to curve, and this curvature influences the motion of other objects. However, the equations of general relativity also allow for the possibility of a cosmological constant, a term that Einstein initially introduced and later dismissed to keep the universe static. The cosmological constant represents a uniform energy density that fills space uniformly, exerting a repulsive force that could, in principle, cause the universe to expand. When the accelerating expansion of the universe was discovered, the cosmological constant was revived as a possible explanation for dark energy. In this context, dark energy is often equated with the cosmological constant, representing a constant energy density that exists throughout the universe. However, the nature of this energy and why it has the value it does remain deeply mysterious. The most straightforward interpretation of the cosmological constant is that it represents the energy of the vacuum itself, often referred to as vacuum energy. According to quantum field theory, even empty space is not truly empty but is filled with temporary, virtual particles that constantly pop in and out of existence. These particles contribute to the vacuum energy, which, when inserted into the equations of general relativity, leads to an accelerated expansion of space. Yet, this explanation is not without its problems. Theoretical calculations of the vacuum energy from quantum field theory yield a value that is astonishingly larger than what is observed, by a factor of 10^11 to 20, the so-called cosmological constant problem. This discrepancy is one of the most significant unsolved problems in physics and suggests that our current understanding of dark energy E, and perhaps even the nature of space and time, is incomplete. Alternative theories have been proposed to explain dark energy, some of which suggest that the cosmological constant may not be constant after all. One such theory is quintessence, which posits that dark energy is not a fixed energy density, but rather a dynamic field that evolves over time. Unlike the cosmological constant, which remains constant throughout the history of the universe, quintessence would change its energy density as the universe expands. This could lead to different scenarios for the future of the universe, depending on how the field evolves. If quintessence weakens over time, the universe's expansion could eventually slow down or even reverse, leading to a big crunch. Conversely, if it strengthens, it could lead to a big rip, where the fabric of space-time is torn apart. To further complicate matters, some theories suggest that our understanding of gravity itself may need to be modified. In these modified gravity theories, dark energy might not exist as a separate entity, but could instead arise from changes to the laws of gravity on cosmological scales. For example, in theories such as FR gravity or brane world models, the effects attributed to dark energy emerge from additional terms in the gravitational equations or from the influence of extra dimensions of space. These theories are still highly speculative and face significant challenges in fitting observational data, but they highlight the possibility that dark energy might be a sign that our current theories of gravity are incomplete. The study of dark energy is a rapidly advancing field, driven by both theoretical work and observational efforts to measure the expansion rate of the universe with increasing precision. One of the most important tools in this effort is the cosmic microwave background, CMB, the afterglow of the Big Bang that provides a snapshot of the universe when it was just 380,000 years old. The CMB encodes information about the early universe's composition, temperature, and density fluctuations, which can be used to infer the universe's expansion history. Data from missions such as NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck satellite have provided some of the most precise measurements of the CMB, helping to constrain the properties of dark energy and refine our models of cosmology. In addition to the CMB, large-scale surveys of galaxies and galaxy clusters are critical for studying dark energy. These surveys map the distribution of matter in the universe and track the growth of cosmic structures over time. By comparing the observed distribution of galaxies with theoretical predictions, scientists can test different models of dark energy and gravity. Projects like the Dark Energy Survey, DES, and the upcoming Euclid mission are designed to probe the effects of dark energy on the universe's large-scale structure, providing valuable data to distinguish between competing theories. Another promising avenue of research involves measuring the expansion rate of the universe, known as the Hubble constant, through different methods. While traditional methods rely on supernova observations, newer techniques involve measuring the gravitational waves from merging neutron stars, an approach known as standard sirens. The LIGO and Virgo observatories have already detected several such events, and future observations could provide an independent measurement of the Hubble constant, offering new insights into the nature of dark energy. Despite these advances, many challenges remain in the study of dark energy. One of the most pressing issues is the tension between different measurements of the Hubble constant, with some methods yielding higher values than others. This discrepancy, known as the Hubble tension, could hint at new physics beyond the standard cosmological model, possibly related to dark energy. Resolving this tension will require more precise measurements and a better understanding of potential systematic errors in current observations. The implications of dark energy extend far beyond the confines of cosmology. If dark energy continues to drive the accelerated expansion of the universe, it will determine the ultimate fate of the cosmos. In a scenario where dark energy remains constant, the universe will continue to expand forever, with galaxies moving farther apart and stars gradually burning out, leading to a cold, dark, and empty universe, a big freeze. Alternatively, if dark energy increases in strength, it could lead to a catastrophic Big Rip, where galaxies, stars, planets, and even atoms are torn apart as space itself expands at an ever-increasing rate. Understanding dark energy is not only crucial for cosmology, but also for our broader understanding of the fundamental forces of nature. It challenges our theories of gravity, quantum mechanics, and the very nature of space and time. Solving the mystery of dark energy could open up new realms of physics, providing insights into phenomena such as quantum gravity, the unification of forces, and the origins of the universe. As researchers continue to explore the depths of the universe, the study of dark energy will undoubtedly play a central role in shaping our understanding of the cosmos. Whether it leads to a deeper understanding of the cosmological constant, the discovery of a new dynamic field like quintessence, or a radical revision of gravity itself, dark energy represents one of the greatest frontiers in modern science. As we unravel the secrets of dark energy, we are reminded that the universe is full of surprises and that our quest for knowledge is far from over. The search for dark energy is deeply connected to other cosmic mysteries, such as dark matter, black holes, and the nature of time itself. As we move forward, the answers we seek may well lead us to new questions, driving humanity ever closer to understanding the true nature of the universe. This journey, while daunting, holds the promise of discoveries that could forever change our view of the cosmos and our place within it, as we turn our gaze toward the next great enigma, the mysterious and powerful black holes that punctuate the fabric of space and time. In the vast expanse of the universe, few phenomena captivate the imagination and challenge our understanding of physics as profoundly as black holes. These enigmatic objects, born from the collapse of massive stars, possess gravitational forces so intense that nothing, not even light, can escape their grasp. As a result, black holes are shrouded in mystery, their true nature hidden behind an event horizon that marks the boundary beyond which no information can return. Yet, despite their elusive nature, black holes play a crucial role in shaping the cosmos, influencing the formation of galaxies, the behavior of matter and energy, and even the flow of time itself. Understanding black holes is not merely a matter of academic curiosity. It is key to unlocking some of the deepest secrets of the universe. A black hole forms when a massive star exhausts its nuclear fuel and can no longer support itself against the pull of gravity. Without the outward pressure from nuclear fusion to counterbalance gravity, the star's core collapses, causing its mass to be concentrated into an infinitesimally small point known as a singularity. At the singularity, density becomes infinite, and the laws of physics as we currently understand them break down. Surrounding this singularity is the event horizon, a spherical boundary beyond which the escape velocity exceeds the speed of light. This means that once something crosses the event horizon, it is irrevocably drawn into the black hole, unable to communicate with the outside universe. The concept of a black hole is deeply rooted in the theory of general relativity, proposed by Albert Einstein in 1915. General relativity describes gravity not as a force between masses, as in Newtonian physics, but as the curvature of space-time caused by the presence of mass and energy. In the case of a black hole, the curvature of space-time becomes so extreme that it creates a region where space and time are effectively sealed off from the rest of the universe. The event horizon represents the point of no return, where space-time curves to an infinite degree. One of the most fascinating aspects of black holes is their impact on time. According to general relativity, time flows differently in strong gravitational fields, a phenomenon known as gravitational time dilation. Near a black hole, time slows down relative to an observer at a safe distance. This effect becomes more pronounced as one approaches the event horizon. From the perspective of a distant observer, an object falling into a black hole appears to slow down and asymptotically freeze at the event horizon, while from the perspective of the object itself, time continues to pass normally as it crosses the threshold. Despite their ominous reputation, black holes are not cosmic vacuum cleaners that indiscriminately devour everything in their vicinity. Instead, they are typically surrounded by accretion disks, rotating disks of gas, dust, and other material that spirals toward the event horizon. As this material accelerates and heats up, it emits radiation, often in the form of X-rays, which can be detected by telescopes. The study of accretion disks and the radiation they emit provides valuable insights into the properties of black holes, including their mass and spin. In fact, the first indirect evidence for black holes came from the observation of X-ray binaries, systems where a star orbits a compact object that is too massive to be a neutron star, but emits X-rays as it accretes material from its companion. In recent years, our understanding of black holes has been revolutionized by direct observations. Perhaps the most groundbreaking discovery was the detection of gravitational waves, ripples in the fabric of space-time, by the LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo collaborations. In 2015, LIGO made the first ever detection of gravitational waves from the merger of two black holes, a discovery that confirmed a key prediction of general relativity and provided direct evidence for the existence of black holes. These gravitational waves carry information about the mass, spin, and even the shape of the black holes involved in the merger, offering a new way to study these mysterious objects. Another monumental achievement came in 2019 when the Event Horizon Telescope (EHT) collaboration released the first ever image of a black hole. This image, showing the shadow of the supermassive black hole at the center of the galaxy M87, was a triumph of both technology and collaboration. The EHT combined data from a network of radio telescopes around the world, effectively creating a planet-sized telescope capable of resolving the tiny region around the black hole's event horizon. The image revealed a bright ring of light, the result of photons orbiting the black hole just outside the event horizon, surrounding a dark central region where the black hole resides. This observation provided the strongest visual evidence to date for the existence of black holes and offered a new way to test the predictions of general relativity in the extreme environment near an event horizon. Black holes come in different sizes, ranging from stellar mass black holes, formed from collapsing stars with masses a few times that of the Sun, to supermassive black holes, which reside in the centers of galaxies and have masses ranging from millions to billions of times that of the Sun. The formation of supermassive black holes is still a subject of intense research, with several competing theories. Some suggest that they formed from the direct collapse of massive clouds of gas in the early universe, while others propose that they grew from smaller black holes through accretion and mergers over billions of years. Regardless of their origin, supermassive black holes are thought to play a crucial role in the evolution of galaxies. Observations have shown that the mass of a supermassive black hole is closely correlated with the mass of the galaxy's bulge, suggesting a co-evolutionary relationship between black holes and their host galaxies. The study of black holes also raises profound questions about the nature of information and the fundamental laws of physics. One of the most puzzling issues is the black hole information paradox, which arises from the apparent contradiction between general relativity and quantum mechanics. According to general relativity, information that falls into a black hole is lost forever once it crosses the event horizon. However, this conflicts with the principles of quantum mechanics, which dictate that information must be conserved. This paradox has led to significant debate and research, with some proposing that information is somehow encoded in the radiation emitted by the black hole, known as Hawking radiation, while others suggest that new physics may be needed to resolve the issue. Hawking radiation, predicted by physicist Stephen Hawking in 1974, is a theoretical process by which black holes can slowly lose mass and eventually evaporate. According to quantum field theory, pairs of virtual particles are constantly being created and annihilated in the vacuum of space. Near the event horizon of a black hole, one of these particles can fall into the black hole while the other escapes, effectively stealing energy from the black hole and causing it to lose mass. While Hawking radiation has yet to be observed directly, partly because it is incredibly weak for all but the smallest black holes, it has profound implications for our understanding of black holes and quantum mechanics. It suggests that black holes are not entirely black but can emit radiation and potentially reveal information about their contents over incredibly long timescales. As we continue to probe the mysteries of black holes, we are likely to uncover new physics that could reshape our understanding of the universe. The study of black holes offers a unique testing ground for theories of quantum gravity, which seek to unify general relativity with quantum mechanics. Observations of black holes, particularly through gravitational waves and the Event Horizon Telescope, will provide increasingly precise tests of these theories, potentially revealing new insights into the fundamental nature of space-time, gravity, and matter. The implications of black holes extend beyond the realm of theoretical physics and into the broader context of the universe's evolution and the fate of its inhabitants. Black holes are key players in the cosmic drama, influencing the formation and growth of galaxies, driving the most energetic processes in the universe, and serving as the engines behind quasars and other active galactic nuclei. Understanding black holes is essential for understanding the life cycle of galaxies, the distribution of matter in the universe, and the ultimate fate of stars and planets. Moreover, black holes challenge our perceptions of reality, space, and time. They force us to confront the limits of our knowledge and the boundaries of the universe itself. As we push the frontiers of black hole research, we are likely to encounter new questions that will drive the next generation of scientific exploration. In conclusion, Black holes are among the most fascinating and important objects in the universe, offering insights into the fundamental nature of gravity, space-time, and the evolution of the cosmos. Through observations, theoretical work, and technological advancements, we have made significant progress in understanding these enigmatic objects, yet many mysteries remain. The study of black holes will continue to be a central focus of astrophysics and cosmology, as we seek to unravel their secrets and understand their role in the broader tapestry of the universe. As we ponder the mysteries of black holes, we find ourselves inevitably drawn to the larger questions they raise about the nature of the universe itself. What lies beyond the event horizon? How do black holes influence the fate of galaxies and the universe? And how does our understanding of black holes connect with the other great mysteries of the cosmos, such as the nature of dark matter and dark energy? These questions lead us to the next frontier in our exploration of the universe, where the known and unknown collide, and where each discovery brings us closer to a deeper understanding of the cosmos. The origin of the universe is a question that has intrigued humanity for millennia, touching on the deepest aspects of existence and the nature of reality itself. Central to our current understanding of the universe's birth is the Big Bang theory, which posits that the universe began as an incredibly hot and dense point, approximately 13.8 billion years ago, before expanding rapidly in a process known as cosmic inflation. However, as we peer further back in time, approaching the very moment of the Big Bang, we encounter a singularity, a point where our current physical theories, including general relativity, break down. This singularity presents not only a limit to our understanding, but also a profound mystery. What, if anything, existed before the Big Bang? This question touches the very edges of modern cosmology and drives numerous speculative theories that attempt to describe the state of the universe before the dawn of time as we know it. At the heart of the Big Bang theory is the concept of a singularity, a point in space-time where density and temperature become infinite. The singularity is a feature predicted by general relativity, which describes how matter and energy influence the curvature of space-time. Under normal conditions, this framework works exceptionally well, describing everything from the orbit of planets to the behavior of light near massive objects. However, as we trace the universe back to its earliest moments, we find that the equations of general relativity yield nonsensical results, such as infinite curvature and density at the singularity. This breakdown suggests that general relativity, while powerful, is incomplete, especially when applied to the extreme conditions of the early universe. The concept of a singularity implies a point where our conventional understanding of physics ceases to be applicable. Time and space as we know them become meaningless, raising the question of whether before the Big Bang even makes sense in the context of time. In classical general relativity, the Big Bang is often described as the beginning of time itself, with no before to speak of. However, this perspective has been challenged by various theoretical developments, particularly those involving quantum mechanics, which governs the behavior of particles at the smallest scales. One of the most promising approaches to resolving the singularity problem is through the theory of quantum gravity, which seeks to unify general relativity with quantum mechanics. While a complete theory of quantum gravity remains elusive, several candidate theories provide potential insights into what might have preceded the Big Bang. Among these is string theory, which posits that the fundamental constituents of the universe are not point-like particles, but rather tiny, vibrating strings. In the framework of string theory, the concept of a singularity could be replaced by a more nuanced understanding of space-time, where the extreme conditions at the Big Bang are smoothed out by the effects of quantum mechanics. Another leading candidate for a theory of quantum gravity is loop quantum gravity, which suggests that space-time itself is quantized, composed of discrete loops that give rise to a granular structure at the smallest scales. In this context, the Big Bang might be reinterpreted as a big bounce, where a previous contracting universe reached a minimum size before rebounding into the expanding universe we observe today. This model suggests that the universe is cyclic, undergoing endless cycles of expansion and contraction, with each big bounce serving as a rebirth of the cosmos. These theories challenge the notion of a singular beginning, suggesting instead that the universe might have an infinite past, with the Big Bang representing just one phase in a much larger cosmic history. However, these ideas remain speculative, as they are difficult to test with current observational technology. Nevertheless, they provide intriguing possibilities for what might have existed before the Big Bang, and they highlight the limitations of our current understanding. In addition to quantum gravity theories, other speculative ideas explore different ways of understanding the pre-Big Bang universe. One such concept is the multiverse, which posits that our universe is just one of many, potentially an infinite number, existing within a larger multiverse. In this scenario, the Big Bang might have been the result of a collision or interaction between different apocket universes, or it might represent the birth of our particular universe from a larger cosmic landscape. The multiverse concept is often linked with inflationary theory, which describes the rapid expansion of the universe in its earliest moments. Some versions of inflationary theory suggest that inflation is an eternal process, continually creating new universes within an ever-expanding multiverse. The idea of the multiverse, while speculative, is compelling because it offers a potential explanation for why our universe has the specific properties it does, properties that seem fine-tuned to allow for the existence of life. If there are countless other universes with different physical laws and constants, it could be that we happen to live in one where the conditions are just right for life to emerge. However, the multiverse theory also faces significant challenges, particularly in terms of empirical verification. By its very nature, the multiverse may be inaccessible to direct observation, making it difficult to test scientifically. In addition to these theoretical developments, recent advances in observational cosmology have provided new insights into the early universe, offering potential clues about what might have preceded the Big Bang. One of the most significant discoveries in this area is the detection of the cosmic microwave background, CMB, the afterglow of the Big Bang that permeates the universe. The CMB provides a snapshot of the universe when it was just 380,000 years old, revealing its temperature fluctuations and the seeds of the large-scale structures we observe today. Detailed measurements of the CMB, particularly those made by missions such as the Planck satellite, have allowed cosmologists to refine models of the early universe and test predictions of inflationary theory. However, the CMB also raises new questions. For example, the horizon problem refers to the observation that different regions of the CMB, which are too far apart to have ever been in causal contact, have nearly identical temperatures. This problem is one of the key motivations for inflationary theory, which suggests that a period of rapid expansion could have stretched the universe so much that these regions were once close enough to exchange information. Yet, if inflation is correct, it might also imply the existence of a multiverse, further complicating our understanding of what happened before the Big Bang. Another intriguing observational challenge is the search for primordial gravitational waves, ripples in space-time produced by the rapid expansion of the early universe. These gravitational waves could provide direct evidence for inflation and, by extension, insights into the conditions that existed before the Big Bang. Experiments such as the BICEP and LIGO collaborations are actively searching for these signals, though their detection remains a formidable challenge. As we continue to probe the mysteries of the early universe, we are likely to encounter new challenges and surprises that will reshape our understanding of cosmic origins. The study of what came before the Big Bang is not just about uncovering the past. It is about exploring the fundamental nature of reality, the origins of time and space, and the ultimate fate of the universe. Whether through the development of new theoretical frameworks, the refinement of existing models, or the discovery of new observational evidence, the quest to understand the pre-Big Bang universe will undoubtedly drive the next generation of cosmological research. In summary, the question of what existed before the Big Bang touches on some of the most profound and challenging aspects of modern science, From the potential insights offered by quantum gravity theories and the multiverse, to the tantalizing clues provided by the cosmic microwave background and the search for primordial gravitational waves, this field of study pushes the boundaries of our knowledge and our imagination. While many questions remain unanswered, the pursuit of these answers will continue to inspire and challenge scientists as they seek to uncover the deepest secrets of the cosmos. As we contemplate the mysteries of the universe's origins, we find ourselves naturally drawn to the broader implications of these questions. What does the existence of a multiverse, if real, mean for our understanding of reality? How does the concept of time itself change if the universe has no true beginning? These questions lead us to the next great frontier in our exploration of the cosmos, where the study of dark matter, black holes, and other fundamental phenomena will continue to reveal the hidden structures and forces that shape our universe. The journey of discovery is far from over, and with each new insight, we move closer to answering the ultimate question: what is the true nature of the universe, and how did it all begin? The question of whether humanity is alone in the universe has fascinated scientists, philosophers, and the general public for centuries. The possibility of life beyond Earth touches on some of the most profound questions about our place in the cosmos and the nature of life itself. Advances in astronomy, biology, and planetary science have made the search for extraterrestrial life one of the most exciting and active areas of scientific inquiry. As we continue to discover new exoplanets, refine our understanding of the conditions necessary for life, and develop technologies capable of detecting potential biosignatures, the prospect of finding life elsewhere in the universe seems more plausible than ever before. However, despite these advances, we have yet to find definitive evidence of extraterrestrial life, leaving the question tantalizingly open. Are we alone in the universe? To understand the search for extraterrestrial life, it is essential to first consider the criteria that scientists use to determine the habitability of other worlds. Life, as we know it, requires a specific set of conditions to thrive. These include the presence of liquid water, a stable climate, an energy source, and a suitable range of chemical elements. On Earth, these conditions are met by the planet's position in the so-called habitable zone around the Sun, where temperatures allow for the existence of liquid water on the surface. This concept of a habitable zone, sometimes referred to as the Goldilocks zone, has been a key factor in the search for potentially life-supporting exoplanets. The discovery of exoplanets, planets orbiting stars outside our solar system, has revolutionized our understanding of the potential for life elsewhere in the universe. Since the first confirmed detection of an exoplanet in 1992, thousands of these distant worlds have been identified, with a significant number located within their star's habitable zone. Some of the most promising candidates include planets such as Proxima Centauri b, which orbits the closest star to the Sun, and the TRAPPIST-1 system, which hosts several Earth-sized planets within its habitable zone. These discoveries have fueled optimism that life could exist on other worlds, particularly on those that share similarities with Earth. However, the mere presence of a planet within a habitable zone does not guarantee that it can support life. Other factors, such as the planet's atmosphere, magnetic field, and geological activity, play crucial roles in maintaining a stable environment that can sustain life. For example, Earth's magnetic field protects the planet from harmful solar radiation, while plate tectonics contribute to the long-term stability of the climate by regulating carbon dioxide levels. Without these features, a planet might become inhospitable even if it lies within the habitable zone. To assess the habitability of exoplanets, scientists use a variety of observational techniques and instruments. One of the most successful methods for detecting exoplanets is the transit method, which involves observing the slight dimming of a star's light as a planet passes in front of it. This technique, used by the Kepler Space Telescope and, more recently, the Transiting Exoplanet Survey Satellite, TESS, has led to the discovery of thousands of exoplanets, including many in the habitable zone. By analyzing the light from these transits, astronomers can infer a planet's size, orbital period, and in some cases, the composition of its atmosphere. The study of exoplanet atmospheres is particularly important in the search for extraterrestrial life. Certain gases, such as oxygen, methane, and carbon dioxide, can be considered potential biosignatures, indicators of biological activity. On Earth, for example, the presence of oxygen in the atmosphere is a direct result of photosynthesis by plants and other organisms. Similarly, methane can be produced by microbial life, though it can also be generated through geological processes. Detecting these gases in the atmosphere of an exoplanet could suggest the presence of life, but distinguishing between biological and non-biological sources remains a significant challenge. The search for biosignatures is a key focus of current and future space missions. The James Webb Space Telescope, JWST, launched in December 2021, is equipped with instruments capable of analyzing the atmospheres of exoplanets in unprecedented detail. By studying the spectra of these atmospheres, JWST can detect the presence of key molecules and assess their potential as indicators of life. Similarly, upcoming missions like the European Space Agency's Ariel, Atmospheric Remote Sensing Infrared Exoplanet Large Survey, and NASA's LUVOIR, Large Ultraviolet Optical Infrared Surveyor, aim to expand our ability to characterize exoplanet atmospheres and search for signs of life. While the search for life on exoplanets is a major focus of astrobiology, our own solar system also offers promising sites for the potential discovery of extraterrestrial life. Among the most intriguing candidates are the icy moons of Jupiter and Saturn, particularly Europa and Enceladus. Beneath their icy surfaces, both moons are believed to harbor subsurface oceans of liquid water, kept warm by tidal heating generated by their interactions with their parent planets. In 2018, NASA's Hubble Space Telescope detected evidence of plumes of water vapor erupting from the surface of Europa, suggesting that its ocean might be in contact with the moon's rocky mantle, a key condition for the potential development of life. In response to these findings, NASA has planned several missions to explore these icy worlds more closely. The Europa Clipper mission, set to launch in the 2020s, will conduct detailed reconnaissance of Europa's surface and subsurface using ice-penetrating radar, magnetometry, and spectrometry to study the moon's ice shell and ocean. Similarly, the proposed Enceladus Life Finder ELIF mission aims to analyze the composition of the plumes on Enceladus, searching for organic molecules and other potential indicators of life. These missions could provide crucial evidence about the habitability of these moons and the possibility of life within our own solar system. The search for extraterrestrial life is not limited to the detection of biosignatures or habitable environments. Another approach, known as the search for extraterrestrial intelligence, SETI, involves listening for signals from advanced civilizations. The idea behind SETI is that intelligent beings, if they exist elsewhere in the galaxy, might use radio waves or other forms of electromagnetic communication to reach out to other civilizations. Since the 1960s, various SETI projects have used radio telescopes to scan the skies for such signals, though none have been detected so far. The Breakthrough Listen initiative, launched in 2015, is one of the most ambitious SETI projects to date, employing state-of-the-art technology to search for signs of intelligent life across a broad range of frequencies. Despite decades of searching, SETI has yet to find any evidence of extraterrestrial intelligence. This lack of success has led to various hypotheses to explain the so-called Great Silence. One possibility is that intelligent civilizations are exceedingly rare, either because life itself is rare or because civilizations tend to self-destruct before they can communicate with others. Another hypothesis is that civilizations might use communication methods that we have yet to discover or understand, making their signals undetectable by our current technology. The Fermi paradox, named after physicist Enrico Fermi, encapsulates this dilemma. If intelligent life is common in the universe, why have we not yet observed any evidence of it? The search for extraterrestrial life, whether microbial or intelligent, carries profound implications for our understanding of life, the universe, and our place within it. If we were to find even the simplest forms of life beyond Earth, it would suggest that life might be a common occurrence in the universe, potentially existing in many forms and under a wide range of conditions. Such a discovery would have profound implications for biology, challenging our understanding of the origins and diversity of life and possibly leading to the recognition of life forms with biochemistries radically different from our own. Conversely, if our search continues to yield no evidence of extraterrestrial life, it could imply that life is an exceedingly rare phenomenon, with Earth being a unique oasis in an otherwise lifeless cosmos. This would raise profound philosophical and ethical questions about our responsibility to protect and preserve life on our planet and our approach to exploring and potentially colonizing other worlds. In conclusion, the search for extraterrestrial life is one of the most ambitious and far-reaching endeavors in science. It spans disciplines from astronomy to biology, from planetary science to philosophy, and it challenges us to think beyond the confines of our own planet. As we continue to explore the universe, both within our solar system and beyond, the question of whether we are alone will remain at the forefront of scientific inquiry. Whether we find life or not, the journey itself will deepen our understanding of the universe and our place within it. As we contemplate the possibility of life elsewhere in the cosmos, we are naturally led to consider the environments that might support such life. This brings us to the fascinating study of extremophiles, organisms that thrive in conditions once thought too harsh for life. Understanding how life can exist in extreme environments on Earth provides crucial insights into where and how we might find life elsewhere in the universe, guiding our search for extraterrestrial life in ways we are only beginning to explore. Time, an ever-present yet elusive dimension, governs our existence and shapes the universe's fundamental structure. From the ticking of a clock to the inexorable march of the seasons, time seems to flow in a single, unchanging direction. However, the true nature of time is far from simple. Is it an absolute, unchanging background against which events unfold, or is it a dynamic entity shaped by the forces of the universe? Does time even exist as we perceive it, or is it merely an illusion created by our limited understanding of reality? These questions lie at the heart of one of the most profound and complex areas of modern science, where physics, philosophy, and cosmology intersect to explore the very fabric of reality. The classical understanding of time, rooted in Newtonian mechanics, portrays it as an absolute, universal entity that flows uniformly, independent of the observer or the events taking place within it. According to Sir Isaac Newton, time is like a vast, unchanging stage upon which the drama of the universe unfolds. This concept of time, known as absolute time, persisted for centuries and formed the foundation of classical physics. In this view, time is linear, with a clear distinction between past, present, and future, and it progresses at the same rate for all observers, regardless of their location or motion. However, this intuitive understanding of time was profoundly challenged in the early 20th century by Albert Einstein's theory of relativity. Einstein's revolutionary ideas reshaped our understanding of time and space, revealing them to be intertwined in a single, four-dimensional continuum known as space-time. In this new framework, time is no longer absolute but relative, depending on the observer's state of motion. According to the theory of special relativity, time dilation occurs when an object approaches the speed of light. The faster an object moves relative to an observer, the more slowly time passes for that object. This effect, though imperceptible at everyday speeds, becomes significant at velocities close to the speed of light, where time can slow to a crawl relative to an outside observer. The implications of time dilation were famously illustrated in the so-called twin paradox, a thought experiment in which one twin travels on a high-speed journey through space while the other remains on Earth. Upon the traveling twins' return, they find that they have aged less than their sibling who stayed behind. This scenario, while paradoxical from a classical perspective, is a natural consequence of special relativity and has been confirmed by experiments involving highly precise atomic clocks flown on aircraft or placed in satellites. The intertwining of time and space in general relativity further complicates our understanding of time. According to this theory, massive objects such as stars and planets warp the fabric of space-time, causing time to flow more slowly in their vicinity. a phenomenon known as gravitational time dilation. This effect is most pronounced near extremely dense objects like black holes, where the curvature of space-time is so intense that time nearly comes to a standstill at the event horizon. For an observer falling into a black hole, time would appear to flow normally, but to a distant observer, their descent would appear to freeze as they approached the event horizon. This bizarre distortion of time challenges our conventional notions of cause and effect, past and future, and underscores the profound impact of gravity on the nature of time itself. Beyond these relativistic effects, time is also deeply connected to the concept of entropy, a measure of disorder or randomness in a system. According to the second law of thermodynamics, entropy tends to increase over time in an isolated system, a principle that gives rise to the arrow of time. This arrow, which points from past to future, is a manifestation of the tendency for systems to evolve from states of lower entropy to higher entropy. In everyday life, this principle explains why processes such as the melting of ice, the mixing of cream into coffee, or the aging of living organisms are irreversible. Once a system has transitioned to a state of higher entropy, it cannot spontaneously return to its original state without external intervention. The connection between entropy and time raises intriguing questions about the origins of the universe and the nature of time itself. If the universe is governed by the second law of thermodynamics, why did it begin in a state of such low entropy, allowing for the emergence of the complex structures we observe today? This question is central to understanding the ultimate fate of the universe. As the universe continues to expand and entropy increases, it will eventually reach a state of heat death, where all available energy is evenly distributed and no further work can be done. In this state of maximum entropy, time as we know it would lose its meaning, as there would be no distinguishable changes or events to mark its passage. While the arrow of time appears to be an inherent feature of our universe, the laws of physics themselves are largely time-symmetric, meaning they do not inherently prefer a direction for the flow of time. This symmetry has led some physicists to speculate that the arrow of time might be a consequence of the initial conditions of the universe, rather than a fundamental property of nature. In this view, the direction of time's flow is determined by the universe's low entropy beginning, with the increase in entropy over time creating the illusion of a forward-moving arrow. Another perspective on time comes from the field of quantum mechanics, which governs the behavior of particles at the smallest scales. Unlike classical physics, where objects have definite positions and velocities, quantum mechanics describes particles in terms of probabilities, with their behavior dictated by the wave function, a mathematical construct that encapsulates all possible outcomes of a quantum system. In quantum mechanics, time plays a crucial role in the evolution of the wave function, but it also introduces puzzling phenomena such as quantum entanglement, where particles separated by vast distances appear to instantaneously influence each other. This spooky action at a distance, as Einstein famously called it, suggests a deep and mysterious connection between time, space, and information that remains poorly understood. One of the most intriguing aspects of quantum mechanics is the concept of superposition, where a particle exists in multiple states simultaneously until it is observed or measured. This raises profound questions about the nature of time and reality. Does time collapse, the wave function, forcing the universe to choose a specific outcome from the many possibilities? Or is time itself an emergent property of a deeper, underlying quantum reality that transcends our conventional understanding? The quest to reconcile quantum mechanics with general relativity, two pillars of modern physics that offer conflicting descriptions of time and space, has led to the development of various theories of quantum gravity, which seek to unify these frameworks into a single coherent theory. Among these is the idea of quantum time, where time is no longer a smooth, continuous flow, but rather a discrete, quantized entity, much like energy levels in an atom. In this view, time might emerge from the fundamental interactions of tiny or indivisible units of space and time, a concept that challenges our everyday perceptions and suggests that time itself could be an illusion or a secondary effect of a more fundamental process. The study of time also intersects with the field of cosmology, where the origins and evolution of the universe provide crucial insights into the nature of time. The Big Bang, which marks the beginning of the observable universe, also represents the beginning of time as we know it. However, the question of what happened before the Big Bang remains one of the most profound mysteries in cosmology. Some theories suggest that time itself may have emerged from a primordial state of timelessness, with the Big Bang representing a transition from a quantum or higher dimensional reality to the universe we inhabit today. Others propose that the Big Bang was not the beginning of time, but rather a bounce or phase transition in an eternal, cyclic universe, where time extends infinitely into the past and future. The implications of these ideas for our understanding of the universe and our place within it are profound. If time is not an absolute, unchanging entity, but rather a relative, dynamic, and possibly emergent phenomenon, then our experience of time as a linear, forward-moving progression may be just one aspect of a much richer, more complex reality. This has profound implications not only for physics, but also for philosophy, as it challenges our most fundamental assumptions about existence, causality, and the nature of reality itself. As we continue to explore the mysteries of time, we are likely to encounter new questions and challenges that will reshape our understanding of the universe. The study of time is not just a matter of academic inquiry. It touches on some of the deepest aspects of human experience and our quest to understand the nature of reality, whether through the development of new theories, the refinement of existing models, or the discovery of new observational evidence. The exploration of time will continue to be a central focus of scientific research, offering new insights into the fundamental structure of the universe. As we delve deeper into the nature of time, we find ourselves inevitably drawn to other fundamental questions about the universe. One such question is whether our universe is the only one, or if it is part of a larger multiverse, where different regions of space-time have different physical properties, histories, and possibly even different versions of time itself. This exploration of the multiverse leads us to the next frontier in our understanding of the cosmos, where the boundaries of our universe blur and we confront the possibility of countless other realities existing alongside our own, each with its own unique laws and mysteries. The journey of discovery is far from over, and with each step, we move closer to unraveling the true nature of the universe and our place within it. The concept of the multiverse, a collection of potentially infinite universes existing beyond our own, is one of the most intriguing and controversial ideas in modern cosmology. While the notion may sound like science fiction, it arises naturally from several well-established theories in physics and cosmology. The multiverse hypothesis challenges our understanding of reality, suggesting that the universe we inhabit might be just one of countless others, each with its own unique properties, physical laws, and histories. This idea not only pushes the boundaries of our imagination, but also forces us to reconsider the very nature of existence, prompting profound questions about the structure of reality and our place within it. The multiverse concept emerges from several different areas of theoretical physics, each offering a distinct version of what a multiverse might entail. One of the most widely discussed versions is the cosmological multiverse, which is closely related to the theory of cosmic inflation. Inflation is a theory that describes a period of extremely rapid expansion in the early universe, occurring within a fraction of a second after the Big Bang. This expansion smoothed out the universe, leading to the homogeneous and isotropic cosmos we observe today. However, inflationary theory also predicts that this rapid expansion might not have occurred uniformly across the entire universe. Instead, it could have been localized, with different regions of space experiencing varying rates of expansion. In this scenario, our observable universe, everything we can see and measure, might be just one bubble in a much larger multiverse of bubble universes. Each of these bubbles could have different physical properties, such as varying values for fundamental constants, different particle physics, or even different numbers of spatial dimensions. These differences would lead to vastly different kinds of universes, some potentially similar to ours and others completely alien. The idea of such a bubble multiverse is a direct consequence of eternal inflation, where inflation continues indefinitely in some regions of space, constantly creating new bubble universes. Another version of the multiverse is rooted in string theory, a theoretical framework that attempts to unify all the fundamental forces of nature into a single, coherent model. String theory suggests that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. One of the remarkable features of string theory is that it requires extra dimensions of space, beyond the familiar three spatial dimensions, in order to be mathematically consistent. These additional dimensions could be compactified, curled up in ways that are invisible at everyday scales, but have profound implications for the structure of the universe. String theory also allows for a vast landscape of possible solutions, each corresponding to a different set of physical laws and constants. This landscape of solutions implies that there could be a multiverse of different universes, each with its own unique set of physical parameters determined by how the extra dimensions are compactified. Some of these universes might support life, while others might be inhospitable, governed by different laws of physics that prevent the formation of complex structures. The string theory multiverse is thus a vast and diverse collection of possible realities, each emerging from the same underlying theoretical framework but realized in different ways. The quantum multiverse, another interpretation, arises from the many worlds interpretation of quantum mechanics. In quantum mechanics, particles exist in a superposition of states until they are observed or measured, at which point the superposition collapses into a single state. The many worlds interpretation, proposed by physicist Hugh Everett in 1957, suggests that all possible outcomes of a quantum measurement actually occur, each in a separate, parallel universe. In this view, every time a quantum event occurs, the universe splits into multiple branches, each representing a different outcome. This leads to a constantly branching multiverse, where every possible history and future exists in parallel. While the many worlds interpretation resolves certain paradoxes in quantum mechanics, such as the Schrödinger's cat thought experiment, it also raises difficult philosophical questions. If every possible outcome occurs in some branch of the multiverse, what does that imply about free will, determinism, and the nature of reality? Moreover, the many worlds interpretation challenges our understanding of probability, as it suggests that all possible outcomes are equally real, existing simultaneously in different universes. Despite the theoretical appeal of the multiverse, one of the biggest challenges is the lack of direct empirical evidence. By definition, other universes in a multiverse would be beyond our observable horizon, making them inaccessible to direct observation. This has led some critics to argue that the multiverse is not a scientific hypothesis, but rather a philosophical or metaphysical one, since it cannot be tested or falsified by experiment. However, proponents of the multiverse argue that certain indirect evidence might be found, such as imprints on the cosmic microwave background, CMB, from collisions between our bubble universe and others, or specific signatures in the distribution of galaxies that could suggest the influence of other universes. Recent advances in observational cosmology have provided some tantalizing hints that could be consistent with a multiverse. For example, the Planck satellite, which mapped the CMB with unprecedented precision, found certain anomalies in the data that some researchers speculate might be evidence of interactions with other bubble universes. However, these anomalies could also be explained by more mundane astrophysical processes, and further investigation is needed to determine whether they indeed point to the existence of a multiverse. In addition to observational challenges, the multiverse hypothesis raises profound philosophical questions. If there are indeed an infinite number of universes, each with its own version of reality, what does that imply about our own universe? Are we just one of countless versions of ourselves, each living out different lives in different realities? This idea can be unsettling, as it suggests that our sense of individuality and uniqueness might be an illusion. Moreover, the concept of an infinite multiverse challenges the principle of Occam's razor, which states that the simplest explanation is usually the correct one. Some argue that the multiverse is an unnecessary complication, introduced to explain phenomena that might be accounted for by other, simpler theories. Nevertheless, the multiverse hypothesis has significant implications for our understanding of the universe and our place within it. If the multiverse exists, it would provide a natural explanation for the fine-tuning of the physical constants in our universe, values that seem remarkably well suited for the existence of life. In a multiverse, where all possible values of these constants are realized in different universes, it is not surprising that we find ourselves in a universe where the conditions are just right for life to develop. This anthropic reasoning, while controversial, offers a potential solution to the problem of fine-tuning without invoking supernatural explanations. The implications of the multiverse extend beyond theoretical physics and cosmology. They challenge our deepest assumptions about reality, causality, and the nature of existence itself. If the multiverse is real, it suggests that reality is far more complex and diverse than we ever imagined, with countless other worlds existing alongside our own, each with its own unique history and future. This idea forces us to reconsider what it means to exist, to be conscious, and to make choices, as every possible outcome of our decisions might be realized in some other universe. As we continue to explore the concept of the multiverse, we are likely to encounter new challenges and questions that will drive the next generation of scientific research. The multiverse represents the frontier of our understanding of the cosmos, pushing the boundaries of what is knowable and what is beyond our reach. Whether or not we ever find definitive evidence for the existence of other universes, the exploration of the multiverse will undoubtedly deepen our understanding of the universe we inhabit and the fundamental principles that govern it. In conclusion, the multiverse hypothesis, while speculative, offers a compelling framework for understanding the diversity and complexity of the cosmos. It arises naturally from several well-established theories in physics, including cosmic inflation, string theory, and quantum mechanics, each suggesting that our universe might be just one of many. While direct evidence for the multiverse remains elusive, the idea has profound implications for our understanding of reality, challenging our notions of individuality, free will, and the nature of existence. As we continue to investigate the multiverse, we may find new insights into the fundamental structure of reality and our place within it. Or we may discover that our universe is indeed unique in ways we have yet to fully comprehend. As we ponder the vast possibilities of the multiverse, we are reminded that our understanding of the universe is still evolving. The search for answers to these profound questions leads us naturally to consider other cosmic mysteries, such as the nature of dark energy and dark matter, enigmatic components that make up the majority of the universe's mass energy content, yet remain largely unexplained. These mysteries continue to challenge and inspire scientists as they seek to unravel the secrets of the cosmos and understand the true nature of the reality we inhabit. The concept of time travel has long captured the imagination of scientists, writers, and the public alike. From H.G. Wells' classic novel, The Time Machine, to the complex narratives of modern science fiction, the idea of moving backward or forward through time continues to fascinate and inspire. But beyond the realm of fiction, the possibility of time travel raises profound questions about the nature of time, causality, and the very fabric of the universe. While time travel remains speculative, advances in physics, particularly in the areas of relativity and quantum mechanics, have provided some intriguing insights into the conditions under which time travel might be possible, as well as the paradoxes and challenges it presents. To understand the scientific basis for time travel, we must first explore the nature of time itself, as described by the theory of relativity. Albert Einstein's theory of special relativity, formulated in 1905, revolutionized our understanding of time and space by showing that they are not separate, absolute entities, but are intertwined in a four-dimensional continuum known as space-time. One of the key insights of special relativity is that the passage of time is relative, depending on the observer's state of motion. This leads to the phenomenon of time dilation, where time moves more slowly for an object in motion relative to a stationary observer. This effect becomes increasingly pronounced as the object approaches the speed of light. Time dilation has been confirmed by numerous experiments, including observations of particles called muons, which decay more slowly when moving at high velocities, and the synchronization of atomic clocks on fast-moving aircraft and satellites. These findings suggest that, at least in theory, traveling at speeds close to the speed of light could allow for a form of time travel into the future, where an astronaut on a high-speed journey might return to find that much more time has passed on Earth than for themselves. However, this form of time travel is unidirectional. It allows movement into the future but not into the past. The possibility of traveling backward in time presents far greater challenges, both theoretically and practically. One of the most widely discussed mechanisms for backward time travel is the concept of a wormhole, also known as an Einstein-Rosen bridge. A wormhole is a hypothetical tunnel-like structure that connects two distant points in space-time, potentially allowing for faster-than-light travel and, under certain conditions, backward time travel. Wormholes are solutions to the equations of general relativity, which describes how gravity arises from the curvature of space-time caused by mass and energy. In principle, if a wormhole could be stabilized and manipulated, it might be possible to create a closed, time-like curve, a path through space-time that returns to its starting point in the past. However, the practical realization of a wormhole faces enormous challenges. For one, creating and stabilizing a wormhole would require exotic matter with negative energy density, a form of matter that has yet to be discovered or created. Additionally, even if such exotic matter were found, the wormhole would likely be unstable and prone to collapse, especially in the presence of any matter attempting to pass through it. Moreover, the creation of closed time-like curves could lead to paradoxes that challenge our understanding of causality, such as the famous grandfather paradox, where a time traveler could theoretically prevent their own existence by altering the past. The grandfather paradox highlights one of the most significant conceptual challenges associated with time travel: the potential violation of causality. Causality is the principle that cause precedes effect, a fundamental aspect of our understanding of the physical world. If backward time travel were possible, it could create situations where an effect precedes its cause, leading to logical contradictions. For example, if a person travels back in time and prevents their grandparents from meeting, they would never be born. Yet if they were never born, they could not have traveled back in time to prevent the meeting. This paradox suggests that either backward time travel is impossible, or our understanding of causality is incomplete. Several theories have been proposed to resolve the paradoxes of time travel. One possibility is the idea of self-consistency, which suggests that any actions taken by a time traveler in the past must be consistent with the already established history. In this view, events unfold in such a way that paradoxes are avoided, and the time traveler cannot change the past in a way that would create a contradiction. Another possibility is the concept of parallel universes, or the many worlds interpretation of quantum mechanics, which posits that every possible outcome of a quantum event occurs in a separate, branching universe. According to this theory, a time traveler who alters the past might simply create a new, parallel timeline, leaving the original timeline unchanged. Despite these theoretical possibilities, the energy requirements and technological challenges of time travel are currently far beyond our reach. For instance, to manipulate a wormhole or create a time machine, we would likely need access to energy levels far exceeding anything we can currently produce. Additionally, the physical effects of time travel, such as the immense gravitational forces near a wormhole, could be catastrophic for any matter attempting to pass through. Even if time travel were theoretically possible, the practical implementation would require breakthroughs in our understanding of physics, as well as advances in technology that are difficult to imagine with our current knowledge. Time travel also has significant implications for our understanding of the universe and the nature of reality. If time travel were possible, it could provide a new way of exploring the cosmos, allowing us to visit distant regions of space in different epochs or even study the evolution of the universe firsthand. It could also open up possibilities for communicating with or observing past civilizations, potentially offering insights into history and culture that would otherwise be lost to time. On a more philosophical level, Time travel challenges our perceptions of free will and determinism. If the future can influence the past, as suggested by some interpretations of time travel, it raises questions about the nature of choice and agency. Are our actions predetermined by a fixed timeline, or do we have the ability to change the course of history through our decisions? The existence of closed time-like curves and the possibility of multiple timelines further complicate these questions, suggesting that the universe might be far more complex and interconnected than we currently understand. While time travel remains a speculative concept, ongoing research in physics continues to explore the boundaries of what is possible within the framework of our current theories. For example, experiments in quantum mechanics have revealed phenomena such as quantum entanglement and superposition, which challenge our classical understanding of time and causality. These discoveries suggest that time may not be as linear or straightforward as it appears in our everyday experience, and that the true nature of time might be deeply intertwined with the underlying quantum structure of the universe. In recent years, there have been proposals for more modest forms of time manipulation, such as chrononautics, which involves the use of advanced technologies to influence the rate at which time passes. For example, researchers have explored the possibility of using high-speed travel or strong gravitational fields to achieve time dilation effects, potentially allowing for long-term space missions where astronauts age more slowly relative to those on Earth. While these technologies are still in the realm of theoretical physics, they represent a step toward understanding and possibly controlling the flow of time. The implications of time travel for the future of humanity are vast. If time travel were ever realized, it could revolutionize our understanding of history, culture, and science, offering new ways to learn from the past and shape the future. However, it would also require careful consideration of the ethical and philosophical consequences, such as the potential for altering historical events or creating unintended consequences in the fabric of reality. The development of time travel would necessitate a new framework for understanding causality, free will, and the nature of existence, challenging us to rethink our place in the universe. In conclusion, time travel is one of the most intriguing and complex concepts in modern science, straddling the boundary between theoretical physics and science fiction. While current understanding suggests that certain forms of time travel might be possible within the framework of relativity and quantum mechanics, the practical realization of time travel faces enormous challenges, both technological and conceptual. The study of time travel not only pushes the limits of our scientific knowledge, but also raises profound questions about the nature of reality, causality, and free will. As we continue to explore the mysteries of time, we may find that our understanding of the universe and our place within it undergoes a fundamental transformation. As we ponder the possibilities of time travel, we are reminded of the many other cosmic mysteries that challenge our understanding, such as the nature of black holes, dark matter, and dark energy. Each of these phenomena, like time travel, pushes the boundaries of our knowledge and invites us to explore the unknown. In this journey of discovery, we continue to seek answers to the deepest questions about the universe, hoping to uncover the hidden truths that govern the cosmos and our existence within it. Antimatter, often referred to as the mirror image of ordinary matter, is one of the most fascinating and enigmatic substances in the universe. Predicted by theoretical physics and later confirmed through experiments, antimatter consists of particles that are identical to those of ordinary matter, but with opposite charges. For instance, the antiparticle corresponding to the electron is the positron, which carries a positive charge instead of a negative one. When matter and antimatter meet, they annihilate each other in a burst of energy, a process that, if harnessed, could potentially provide a nearly limitless source of power. However, despite its theoretical importance and potential applications, antimatter remains rare and elusive, raising profound questions about the nature of the universe and the symmetry of physical laws. The existence of antimatter was first predicted in 1928 by the British physicist Paul Dirac, who developed an equation that combined quantum mechanics and special relativity to describe the behavior of electrons. Dirac's equation revealed that for every particle of matter, there should be a corresponding antiparticle with the same mass but opposite charge. Initially, this result was met with skepticism, as it implied the existence of particles that had never been observed. However, just 4 years later, in 1932, American physicist Carl Anderson discovered the positron while studying cosmic rays, providing the first experimental evidence for antimatter and confirming Dirac's prediction. The discovery of antimatter was a groundbreaking moment in physics, opening up new avenues of research into the fundamental nature of the universe. Antimatter behaves in many ways like ordinary matter, but its interactions with matter are dramatically different. When a particle of matter meets its corresponding antiparticle, they annihilate each other, converting their entire mass into energy according to Einstein's famous equation, E=mc2 EmC2. This annihilation process is extremely efficient, with a single gram of antimatter potentially releasing as much energy as several nuclear bombs. However, this same property also makes antimatter incredibly difficult to store and study, as it must be kept isolated from any contact with matter. The challenge of producing and storing antimatter is compounded by its scarcity in the universe. While antimatter is routinely produced in high-energy environments, such as in particle accelerators or certain astrophysical processes, it exists only fleetingly before annihilating with nearby matter. In the laboratory, scientists have developed sophisticated techniques to create and trap small amounts of antimatter. For example, the European Organization for Nuclear Research, CERN, has built a facility called the Antiproton Decelerator, where antiprotons are produced, slowed down, and stored for study. In 2010, CERN's ALPHA experiment succeeded in trapping antihydrogen atoms, the antimatter counterpart of hydrogen, for the first time, allowing researchers to begin probing the properties of antimatter in more detail. One of the great mysteries surrounding antimatter is why the universe appears to be composed almost entirely of matter, with little to no antimatter present. According to the Big Bang theory, the universe should have begun with equal amounts of matter and antimatter. However, if matter and antimatter were perfectly symmetrical, they would have annihilated each other completely, leaving behind a universe filled only with energy. The fact that we observe a universe dominated by matter suggests that some mechanism must have broken this symmetry, leading to a slight excess of matter over antimatter in the early universe. This asymmetry, known as baryon asymmetry, is one of the most significant unsolved problems in cosmology and particle physics. Several theories have been proposed to explain the matter-antimatter asymmetry, many of which involve processes that occurred in the first moments after the Big Bang. One leading hypothesis is that during the early stages of the universe, certain interactions violated charge parity, CP symmetry, a fundamental symmetry that relates particles to their antiparticles. CP violation has been observed in experiments involving certain subatomic particles called mesons, but the level of CP violation seen in these experiments is not sufficient to account for the observed matter-antimatter imbalance. This suggests that there may be other, as yet undiscovered, sources of CP violation that could explain the dominance of matter in the universe. The study of antimatter and CP violation has been a major focus of experimental particle physics. For example, experiments at CERN's Large Hadron Collider, LHC, and Japan's Super-Key KB accelerator are designed to explore CP violation in greater detail by studying the behavior of particles like B mesons. These experiments aim to uncover new physics beyond the standard model, the current framework that describes the fundamental particles and forces. If new sources of CP violation are discovered, they could provide critical insights into the mechanisms that led to the matter-antimatter asymmetry and the formation of the universe as we know it. In addition to its fundamental importance in understanding the origins of the universe, antimatter also holds potential for revolutionary technological applications. One of the most exciting possibilities is the use of antimatter as a source of energy. Because the annihilation of matter and antimatter releases enormous amounts of energy, even a small amount of antimatter could, in theory, provide a highly efficient power source. This has led to speculation about the use of antimatter in applications ranging from spacecraft propulsion to advanced medical treatments. For instance, antimatter propulsion has been proposed as a means of achieving interstellar travel. Traditional chemical rockets are limited by the amount of fuel they can carry and the relatively low efficiency of chemical reactions. In contrast, an antimatter-powered spacecraft could achieve much higher speeds due to the enormous energy released during matter-antimatter annihilation. This would significantly reduce travel times to distant stars, potentially making interstellar exploration feasible within a human lifetime. However, the practical challenges of producing and storing enough antimatter for such missions are currently insurmountable, and significant technological advancements would be required to make antimatter propulsion a reality. Antimatter also has potential applications in medicine, particularly in the field of cancer treatment. Positron emission tomography, PET, is a well-established medical imaging technique that uses positrons to produce detailed images of the body's internal structures. In PET scans, a radioactive substance that emits positrons is injected into the body. When the positrons encounter electrons in the body, they annihilate, producing gamma rays that can be detected to create images of tissues and organs. This technique is particularly valuable for detecting cancers, monitoring the progress of treatments, and studying brain activity. Beyond imaging, researchers are investigating the possibility of using antiprotons for targeted cancer therapies, exploiting their ability to deposit energy in tissues in a controlled manner before annihilating, potentially leading to more effective treatments with fewer side effects. Despite the potential benefits, the use of antimatter in practical applications is still in its infancy. The primary obstacle is the extremely high cost and difficulty of producing antimatter. Currently, producing even a tiny fraction of a gram of antimatter would require enormous amounts of energy and financial resources. For example, it has been estimated that producing 1 gram of antimatter would cost hundreds of trillions of dollars at current production rates. As a result, most research on antimatter remains focused on fundamental physics rather than practical applications. The exploration of antimatter also has broader implications for our understanding of the universe and the laws that govern it. By studying the properties of antimatter and its interactions with matter, scientists hope to gain deeper insights into the fundamental symmetries of nature, the behavior of particles at the quantum level, and the processes that shape the early universe. Antimatter research is closely linked to other cutting-edge areas of physics, such as the search for dark matter, the investigation of black holes, and the study of cosmic rays. These connections highlight the central role that antimatter plays in the broader quest to understand the fundamental nature of reality. In conclusion, antimatter is a substance that challenges our understanding of the universe, offering both profound mysteries and tantalizing possibilities. From its prediction by Dirac to its discovery by Anderson, antimatter has played a key role in shaping modern physics, leading to new insights into the symmetry and structure of the universe. Despite its rarity and the significant challenges associated with its production and storage, antimatter continues to be a focus of scientific research, with potential applications in energy production, space exploration, and medicine. As scientists continue to probe the properties of antimatter and explore its interactions with matter, they are likely to uncover new phenomena and deepen our understanding of the cosmos. As we contemplate the mysteries of antimatter, we are reminded of the many other enigmatic forces and substances that permeate the universe, such as dark matter and dark energy. These unseen components make up the majority of the universe's mass energy content, yet they remain largely unexplained, posing some of the greatest challenges to modern cosmology. The study of antimatter, with its unique properties and potential to unlock new physics, may one day provide clues that help us unravel these larger cosmic mysteries, bringing us closer to a complete understanding of the universe and our place within it. The structure of space-time, a concept introduced by Albert Einstein's theory of general relativity, forms the very fabric of our universe, weaving together the dimensions of space and time into a single, unified continuum. Unlike the static, unchanging backdrop that space and time were once thought to be, space-time is dynamic, bending and warping in response to the presence of mass and energy. This curvature is what we perceive as gravity, a force that governs the motion of planets, stars, and galaxies, and shapes the large-scale structure of the cosmos. Understanding the nature of space-time and its interactions with matter and energy is fundamental to our comprehension of the universe, from the motion of celestial bodies to the behavior of black holes and the expansion of the universe itself. At the core of general relativity is the idea that gravity is not a force in the traditional sense, but rather a manifestation of the curvature of space-time. Massive objects, such as stars and planets, cause space-time to curve around them, creating what we experience as gravitational attraction. The more massive an object, the greater the curvature it induces, and thus the stronger its gravitational pull. This revolutionary concept replaced the Newtonian view of gravity, which treated it as a force acting at a distance, and provided a new framework for understanding the motion of objects in the universe. The curvature of space-time is described mathematically by Einstein's field equations, a set of 10 interrelated differential equations that relate the distribution of matter and energy in the universe to the curvature of space-time. These equations are highly complex, and their solutions describe how space-time is shaped by the presence of matter and energy. One of the most famous solutions to Einstein's field equations is the Schwarzschild solution, which describes the space-time around a spherically symmetric, non-rotating mass, such as a simple black hole. This solution predicts the existence of an event horizon, a boundary beyond which nothing, not even light, can escape the gravitational pull of the black hole. The concept of space-time curvature has been confirmed by numerous experiments and observations. One of the earliest and most famous confirmations came during the solar eclipse of 1919, when British astronomer Sir Arthur Eddington observed the bending of starlight as it passed near the Sun. This observation was the first direct evidence that gravity could bend light, a phenomenon known as gravitational lensing. Since then, gravitational lensing has become a powerful tool in astrophysics, allowing scientists to study the distribution of dark matter, the properties of distant galaxies, and the expansion of the universe. Gravitational lensing occurs when a massive object, such as a galaxy or a cluster of galaxies, lies between a distant light source and an observer. The gravity of the intervening object bends the light from the source, creating distorted, magnified, or multiple images of the source. This effect has been used to map the distribution of dark matter, which does not emit or absorb light but can be detected through its gravitational influence on visible matter. For example, the Bullet cluster, a collision between two galaxy clusters, provided compelling evidence for the existence of dark matter through the gravitational lensing of background galaxies. Another significant prediction of general relativity is the existence of gravitational waves, ripples in the fabric of space-time, that propagate outward from accelerating masses, such as binary star systems or colliding black holes. These waves were first directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, a discovery that confirmed a key aspect of general relativity and opened up a new era of observational astronomy. Gravitational waves carry information about their sources that is not accessible through electromagnetic radiation, allowing scientists to study phenomena such as black hole mergers and neutron star collisions in unprecedented detail. The discovery of gravitational waves has not only validated general relativity, but also provided a new method for probing the universe. By analyzing the signals from gravitational waves, scientists can infer the properties of the objects involved in the event, such as their masses, spins, key, and distances from Earth. For example, the first detection of gravitational waves, GW15094, was produced by the merger of two black holes with masses about 29 and 36 times that of the Sun. The detection of these waves confirmed the existence of stellar mass black holes and provided direct evidence of their mergers, events that had previously been theorized but never observed. In addition to gravitational waves, the curvature of space-time has profound implications for our understanding of black holes, objects so dense that their gravitational pull creates regions of space-time from which nothing can escape. Black holes are described by solutions to Einstein's field equations, such as the Schwarzschild and Kerr solutions, which describe non-rotating and rotating black holes, respectively. These solutions predict the existence of singularities, points where the curvature of space-time becomes infinite and the laws of physics as we know them break down. The study of black holes has led to significant advancements in our understanding of space-time and gravity. For example, the concept of the event horizon, the boundary beyond which nothing can escape a black hole's gravity, challenges our understanding of causality and information. The information paradoxes, which arises from the apparent loss of information when matter falls into a black hole, has prompted ongoing research into the nature of space-time, quantum mechanics, and the possible resolution of this paradox through theories of quantum gravity. The curvature of space-time also plays a crucial role in the expansion of the universe, a phenomenon first observed by Edwin Hubble in 1929. Hubble's discovery that distant galaxies are receding from us, with their velocities proportional to their distances, provided the first evidence for the expanding universe and led to the development of the Big Bang theory. According to general relativity, the expansion of the universe can be described by solutions to the field equations known as the Friedmann-Lemaitre-Robertson-Walker (FLRW) metric, which models a homogeneous, isotropic universe. This metric describes how the scale factor of the universe changes over time, providing a framework for understanding the evolution of the cosmos from the Big Bang to the present day. The expansion of the universe is influenced by the curvature of space-time, which in turn is determined by the total amount of matter and energy in the universe. Depending on the density of the universe, space-time can have positive curvature, a closed universe, negative curvature, an open universe, or zero curvature, a flat universe. Observations of the cosmic microwave background, CMB, the afterglow of the Big Bang, suggest that the universe is very close to flat, meaning that the geometry of space-time is nearly Euclidean on large scales. This finding has important implications for the ultimate fate of the universe, suggesting that it will continue to expand indefinitely, though at an ever-slowing rate. Recent discoveries have added new layers of complexity to our understanding of space-time and its curvature. In 1998, observations of distant Type Ia supernovae revealed that the expansion of the universe is not slowing down, as had been expected, but is instead accelerating. This discovery led to the proposal of dark energy, a mysterious form of energy that permeates all of space and exerts a repulsive force, counteracting gravity and driving the accelerated expansion. Dark energy is thought to account for about 68% of the total energy content of the universe, but its nature remains one of the biggest mysteries in cosmology. Understanding how dark energy interacts with space-time and contributes to the curvature of the universe is a major focus of current research. The study of space-time curvature has also inspired the search for a unified theory of gravity and quantum mechanics, a theory of quantum gravity that would reconcile general relativity with quantum field theory. One of the leading candidates for such a theory is string theory, which posits that the fundamental building blocks of the universe are not point-like particles, but one-dimensional strings. String theory suggests that space-time may have more than 4 dimensions, with the extra dimensions compactified or hidden at scales too small to detect. Another approach, loop quantum gravity, seeks to quantize space-time itself, proposing that space is composed of discrete units, or loops, at the smallest scales. Both theories aim to explain the behavior of space-time at the Planck scale, where quantum effects are expected to dominate, and where the classical description of space-time as a smooth continuum breaks down. The exploration of space-time and its curvature has profound implications for our understanding of the universe and the nature of reality. The study of space-time not only provides insights into the behavior of celestial objects and the evolution of the cosmos, but also challenges our understanding of fundamental concepts such as causality, information, and the nature of space and time themselves. As we continue to probe the mysteries of space-time, we are likely to encounter new phenomena and deepen our understanding of the universe. from the smallest scales of quantum gravity to the largest structures of the cosmos. In conclusion, the curvature of space-time is a fundamental concept that underpins our understanding of gravity, the behavior of black holes, and the expansion of the universe. From Einstein's theory of general relativity to the latest discoveries in cosmology, the study of space-time has revolutionized our understanding of the universe and opened up new avenues of research into the nature of reality. As we continue to explore the mysteries of space-time, we are likely to uncover new insights into the fundamental laws of physics and the structure of the cosmos, bringing us closer to a unified theory of everything. As we delve deeper into the nature of space-time, we are reminded that our understanding of the universe is still evolving. The study of black holes, dark matter, and dark energy continues to challenge our theories and push the boundaries of what we know. In this journey of discovery, each new insight into the curvature of space-time brings us closer to unraveling the ultimate mysteries of the cosmos, guiding us toward a deeper understanding of the universe and our place within it. The intersection of artificial intelligence, AI, and space exploration represents one of the most transformative advancements in modern science and technology. As humanity pushes the boundaries of what is possible in the exploration of our solar system and beyond, AI is increasingly becoming an indispensable tool. From autonomous rovers traversing the Martian surface to sophisticated algorithms analyzing vast amounts of astronomical data, AI is enabling new discoveries and missions that were previously unimaginable. The integration of AI in space exploration is not only enhancing our ability to explore distant worlds, but also reshaping our understanding of the universe and our place within it. Artificial intelligence, in its most basic definition, refers to the capability of a machine to imitate intelligent human behavior. In the context of space exploration, AI encompasses a wide range of technologies, including machine learning, computer vision, natural language processing, and robotics. These technologies are being deployed to perform tasks that are too complex, dangerous, or time-consuming for humans to handle. The harsh and unpredictable environments of space, combined with the vast distances involved, make AI particularly well-suited for space missions, where autonomy, adaptability, and efficiency are crucial. One of the most prominent examples of AI in space exploration is the use of autonomous rovers on Mars. The Mars rovers, such as NASA's Curiosity and Perseverance, are equipped with sophisticated AI systems that allow them to navigate the Martian terrain, avoid obstacles, and conduct scientific experiments with minimal input from mission control on Earth. Given the significant communication delays, up to 24 minutes round trip between Earth and Mars, these rovers must be capable of making real-time decisions based on their immediate surroundings. AI enables these machines to analyze their environment, select appropriate paths, and even prioritize scientific targets based on predefined criteria. This level of autonomy is essential for maximizing the efficiency and scientific return of these missions. The success of AI-driven rovers has not only advanced our knowledge of Mars, but has also set the stage for future exploration missions. For instance, Perseverance, which landed on Mars in February 2021, is equipped with an AI system known as AEGIS, Autonomous Exploration for Gathering Increased Science, which allows the rover to autonomously target and analyze rocks that may be of scientific interest. This capability reduces the need for constant human oversight and allows the rover to perform more scientific experiments in a shorter amount of time. As AI technology continues to evolve, future missions could see even greater levels of autonomy, with rovers capable of conducting complex scientific investigations and making real-time decisions about where to explore next. Beyond Mars, AI is playing a critical role in the exploration of other celestial bodies and the broader cosmos. In the search for life beyond Earth, AI is being used to analyze data from missions such as the Kepler Space Telescope and its successor, the Transiting Exoplanet Survey Satellite, TESS. These missions have generated massive datasets, identifying thousands of potential exoplanets by detecting the tiny dips in starlight caused by a planet passing in front of its host star. Analyzing this data manually would be an enormous task, but AI algorithms are capable of sifting through the data at incredible speeds, identifying potential exoplanets, and even distinguishing between true planetary signals and false positives caused by other astronomical phenomena. The application of AI in exoplanet research has already led to significant discoveries. For example, in 2018, AI algorithms were used to reanalyze data from the Kepler mission, leading to the discovery of several previously overlooked exoplanets, including some that lie within their star's habitable zone, where conditions might be right for liquid water and potentially life. These discoveries highlight the potential of AI to enhance our understanding of the universe by uncovering hidden patterns and insights that might otherwise go unnoticed. In addition to discovering new worlds, AI is also being used to study the vast structures and dynamics of our universe. One of the most significant challenges in modern astronomy is the analysis of large-scale surveys of the cosmos, which can generate petabytes of data. Projects such as the Sloan Digital Sky Survey, SDSS, and the upcoming Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, aim to map the universe in unprecedented detail, capturing billions of celestial objects over the course of their operations. AI and machine learning algorithms are essential tools in processing and analyzing this data, enabling astronomers to identify and classify galaxies, supernovae, and other cosmic phenomena with high accuracy and efficiency. AI's ability to analyze large datasets is also being leveraged in the search for signals from extraterrestrial civilizations, a field known as the Search for Extraterrestrial Intelligence, SETI. Traditionally, SETI has relied on the manual analysis of radio signals from space, searching for patterns that might indicate the presence of intelligent life. However, the vastness of the search field and the sheer volume of data have made this approach increasingly impractical. AI algorithms, particularly those designed for pattern recognition, are now being employed to sift through this data more effectively, searching for the faint, anomalous signals that could indicate the presence of an extraterrestrial civilization. While the benefits of AI in space exploration are clear, the integration of these technologies also presents significant challenges. One of the primary challenges is ensuring the reliability and robustness of AI systems in the harsh and unpredictable environments of space. Space missions are often conducted in extreme conditions, with high levels of radiation, temperature fluctuations, and mechanical stresses that can affect the performance of electronic systems. AI systems must be designed to operate effectively under these conditions, with redundancies and fail-safes in place to prevent catastrophic failures. Additionally, the autonomy of AI systems raises ethical and operational questions about decision-making in space. As AI becomes more capable of making complex decisions, it is crucial to ensure that these decisions align with mission goals and ethical guidelines, particularly in situations where human lives or valuable scientific data are at stake. Another challenge is the need for AI systems to learn and adapt in real time. Unlike Earth-based applications, where AI systems can be regularly updated and retrained with new data, space missions often involve long durations with limited opportunities for intervention. AI systems used in space exploration must be capable of adapting to new and unexpected situations, learning from their experiences, and improving their performance over time. This requires the development of advanced machine learning algorithms and techniques that can operate independently in dynamic environments. Despite these challenges, the future of AI in space exploration looks promising. As AI technology continues to advance, we can expect to see even more sophisticated systems that are capable of performing complex tasks with greater autonomy and efficiency. For example, AI could enable the development of autonomous spacecraft that can navigate through the solar system, conduct scientific experiments, and even repair themselves if damaged. Such capabilities would be particularly valuable for long-duration missions to distant planets, moons, or asteroids, where communication delays and logistical constraints make human oversight difficult or impossible. AI is also likely to play a key role in the future of human space exploration. As humanity prepares to return to the Moon, travel to Mars, and eventually explore other parts of the solar system, AI will be essential for ensuring the safety and success of these missions. AI-powered systems could assist astronauts in a wide range of tasks, from navigation and resource management to medical diagnostics and emergency response. In habitats on the Moon or Mars, AI could help manage life support systems, optimize energy use, and even assist in the construction and maintenance of infrastructure. By reducing the burden on astronauts and enhancing their capabilities, AI will be a critical enabler of sustainable human presence in space. Moreover, AI has the potential to revolutionize the way we think about space exploration itself. With the ability to process and analyze vast amounts of data, AI could help us uncover new patterns and connections in the cosmos, leading to breakthroughs in our understanding of fundamental physics, cosmology, and the origins of life. AI could also enable new forms of exploration, such as the creation of virtual models of distant planets and galaxies, allowing scientists to conduct experiments and simulations that would be impossible to perform in the physical world. In conclusion, the integration of artificial intelligence into space exploration is transforming the way we explore and understand the universe. From autonomous rovers on Mars to AI-driven analysis of astronomical data, these technologies are enhancing our ability to explore distant worlds, discover new phenomena, and push the boundaries of human knowledge. While the challenges of developing and deploying AI systems in space are significant, the potential benefits are immense, offering new opportunities for scientific discovery, technological innovation, and the future of human space exploration. As we look to the future, the continued development of AI in space exploration will be essential for addressing some of the most profound questions in science, such as the search for extraterrestrial life, the nature of dark matter and dark energy, and the origins of the universe itself. The partnership between human ingenuity and machine intelligence is poised to unlock new frontiers in our quest to understand the cosmos, guiding us toward a deeper and more comprehensive understanding of the universe and our place within it. The quest for a theory of everything, too, is one of the most ambitious and profound endeavors in modern physics. This theory would unify all the fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single, coherent framework. The pursuit of such a theory has been a driving force in theoretical physics for decades, promising not only a deeper understanding of the universe's underlying principles, but also the potential to resolve some of the most perplexing mysteries in cosmology and particle physics. Despite significant progress, a complete and experimentally validated theory of everything remains elusive, with many challenges and questions still to be addressed. At the heart of the search for a theory of everything lies the need to reconcile two pillars of modern physics: general relativity and quantum mechanics. General relativity, formulated by Albert Einstein in 1915, describes the force of gravity and the large-scale structure of space-time. It provides a highly accurate description of phenomena such as the motion of planets, the bending of light around massive objects, and the expansion of the universe. However, general relativity is a classical theory, meaning it does not account for the quantum nature of matter at the smallest scales. Quantum mechanics, on the other hand, is the framework that governs the behavior of particles at the atomic and subatomic levels. It describes the fundamental interactions between particles such as electrons, quarks, and photons, and has been remarkably successful in explaining a wide range of phenomena, from the behavior of atoms and molecules to the workings of semiconductors and lasers. Quantum mechanics, and its extension in the form of quantum field theory, forms the basis of the standard model of particle physics, which describes three of the four known fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force, along with the particles that mediate these forces. The challenge arises because general relativity and quantum mechanics are fundamentally incompatible in their current forms. General relativity treats space-time as a smooth, continuous fabric, while quantum mechanics describes nature in terms of discrete, quantized entities. When physicists attempt to apply quantum mechanics to the gravitational field, they encounter mathematical inconsistencies such as infinities that cannot be easily resolved. This incompatibility is most apparent in extreme environments, such as the singularities at the centers of black holes or the conditions of the universe at the moment of the Big Bang, where both quantum effects and strong gravitational fields are significant. To address this incompatibility, physicists have developed several candidate theories for quantum gravity, attempts to unify general relativity and quantum mechanics into a single framework. One of the most prominent of these is string theory, which posits that the fundamental constituents of the universe are not point-like particles, but rather one-dimensional strings that vibrate at different frequencies. These strings can manifest as different particles depending on their vibrational modes, and string theory naturally incorporates gravity by including a particle known as the graviton, which mediates the gravitational force. String theory also introduces the concept of extra dimensions beyond the familiar 3 dimensions of space and 1 of time. In some versions of string theory, these extra dimensions are compactified, or curled up, at scales too small to be detected by current experiments. The theory's mathematical consistency requires these extra dimensions, and it offers the tantalizing possibility of unifying all fundamental forces within a single theoretical framework. However, string theory is not without its challenges. It predicts a vast landscape of possible solutions, known as the string landscape, each corresponding to a different vacuum state with its own set of physical constants and laws. This multitude of possible universes complicates the task of identifying which solution, if any, corresponds to our own universe. Another approach to quantum gravity is loop quantum gravity, LQG, which takes a different route by directly quantizing spacetime itself. LQG suggests that spacetime is composed of discrete, finite loops or spin networks that are woven together to form the fabric of the universe. This theory does not require extra dimensions and remains closer to the traditional principles of general relativity, making it an appealing alternative to string theory. Loop quantum gravity has had some success in describing certain quantum aspects of black holes and the early universe, but it remains an incomplete theory, with many technical challenges still to be resolved. In addition to these theoretical approaches, the search for a theory of everything also involves probing the limits of the standard model of particle physics. While the standard model has been extremely successful in describing the fundamental particles and their interactions, it is widely believed to be incomplete. For example, the standard model does not incorporate gravity, nor does it explain the nature of dark matter and dark energy, which together make up about 95% of the universe's total mass energy content. Furthermore, the discovery of the Higgs boson in 2012, while a major triumph for the standard model, has raised new questions about the stability of the universe and the possibility of new physics beyond the standard model. To explore these questions, physicists are conducting experiments at the frontiers of high-energy physics, such as those at the Large Hadron Collider, LHC, at CERN. The LHC is the world's most powerful particle accelerator, capable of smashing protons together at energies of up to 13 TeV, tera-electron volts. By studying the products of these collisions, physicists hope to uncover evidence of new particles, forces, or phenomena that could point the way to a more complete understanding of the fundamental laws of nature. For example, the detection of supersymmetric particles, hypothetical partners to the known particles, could provide evidence for supersymmetry, a theoretical extension of the standard model that offers a natural unification of forces and a candidate for dark matter. Another promising area of research involves the study of cosmic inflation, a rapid expansion of the universe that is believed to have occurred in the first fractions of a second after the Big Bang. Inflationary theory explains the observed homogeneity and isotropy of the universe and predicts the existence of primordial gravitational waves, ripples in spacetime that would have been generated during inflation. Detecting these gravitational waves would provide a direct probe of the physics of the early universe and could offer clues about the unification of forces at the highest energies. However, despite these efforts, the search for a theory of everything remains fraught with challenges. One of the most significant obstacles is the lack of direct experimental evidence for quantum gravity. The energies required to probe the quantum nature of spacetime are far beyond the reach of current or foreseeable technology. This has led some physicists to explore alternative approaches, such as the holographic principle, which suggests that the information content of a volume of space can be encoded on a lower dimensional boundary, potentially offering a new way to understand gravity and quantum mechanics. The implications of discovering a theory of everything would be profound, both for our understanding of the universe and for the future of science and technology. A unified theory could provide answers to some of the most fundamental questions in physics, such as the nature of space and time, the origins of the universe, and the fate of black holes. It could also lead to new technologies based on principles that are currently beyond our comprehension, with potential applications ranging from quantum computing to advanced propulsion systems for space exploration. Moreover, a theory of everything could have philosophical and existential implications, challenging our understanding of reality and our place in the cosmos. It could offer insights into the nature of consciousness, the possibility of parallel universes, and the ultimate fate of the universe itself. These questions are not only of interest to physicists, but also to philosophers, theologians, and anyone seeking to understand the deeper meaning of existence. In conclusion, the search for a theory of everything represents one of the most ambitious and challenging endeavors in modern science. It involves the unification of general relativity and quantum mechanics, the exploration of new theoretical frameworks, such as string theory and loop quantum gravity, and the pursuit of experimental evidence at the frontiers of high-energy physics and cosmology. While significant progress has been made, many questions remain unanswered, and the path to a complete and experimentally validated theory is likely to be long and complex. As we continue to explore the mysteries of the universe, the quest for a theory of everything will remain a central focus of theoretical physics, guiding our search for new knowledge and deeper understanding. Whether or not we ultimately succeed in finding such a theory, the journey itself will undoubtedly lead to new discoveries and insights that will reshape our understanding of the cosmos and our place within it. This pursuit, driven by the desire to comprehend the fundamental laws of nature, reflects the enduring human quest for knowledge, a quest that, like the universe itself, seems boundless and infinite. The observable universe is a vast and complex network of galaxies, stars, planets, and other celestial bodies, all interconnected through the fabric of space and time. However, beyond the edge of what we can see lies an even greater mystery, the possibility of other universes, each with its own distinct properties and physical laws. This idea, known as the multiverse, challenges our understanding of reality and forces us to reconsider the very nature of existence. While the concept of the multiverse has its roots in theoretical physics and cosmology, it also raises profound philosophical and existential questions that continue to intrigue scientists and laypeople alike. The idea of a multiverse arises from several different areas of physics, each offering a unique perspective on how multiple universes might exist. One of the most compelling arguments for the existence of a multiverse comes from the theory of cosmic inflation, a period of rapid expansion that occurred in the first fraction of a second after the Big Bang. According to inflationary theory, the universe expanded exponentially, smoothing out any initial irregularities and setting the stage for the formation of galaxies and other large-scale structures. However, inflationary theory also suggests that this rapid expansion did not stop everywhere at the same time. Instead, it may have continued in some regions, creating bubble universes that are separate from our own. Each of these bubbles could have different physical properties, such as varying values for the fundamental constants, different particle physics, or even different numbers of spatial dimensions. In this inflationary multiverse, our observable universe is just one bubble in a vast and possibly infinite sea of other universes. Some of these universes might be similar to ours, while others could be radically different, with physical laws that are incompatible with life as we know it. The idea of a multiverse provides a potential explanation for the fine-tuning problem, which refers to the fact that the fundamental constants of nature appear to be precisely calibrated to allow for the existence of life. In a multiverse, It is not surprising that we find ourselves in a universe with the right conditions for life, because there are countless other universes where the conditions are not suitable and no observers are present to question them. Another area of physics that suggests the existence of a multiverse is string theory, a theoretical framework that attempts to unify all the fundamental forces of nature into a single, coherent model. String theory posits that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings can vibrate at different frequencies, giving rise to the various particles and forces that make up the universe. One of the remarkable features of string theory is that it requires extra dimensions beyond the familiar 3 dimensions of space and 1 of time. In some versions of string theory, these extra dimensions are compactified or curled up at scales too small to detect. However, the theory also predicts a vast landscape of possible solutions, each corresponding to a different vacuum state with its own set of physical laws and constants. This string landscape suggests the existence of a multiverse, where each universe corresponds to a different solution in the landscape. The concept of the multiverse is also supported by the many worlds interpretation of quantum mechanics, a theory that provides a radical new way of understanding the behavior of particles at the quantum level. In quantum mechanics, particles do not have definite positions or velocities until they are observed or measured. Instead, they exist in a superposition of all possible states, with each state corresponding to a different outcome. The many worlds interpretation, proposed by physicist Hugh Everett in 1957, suggests that every possible outcome of a quantum event actually occurs, with each outcome realized in a separate, parallel universe. In this view, the universe is constantly branching into multiple copies, with every possible history and future existing simultaneously. While the many worlds interpretation resolves certain paradoxes in quantum mechanics, such as the Schrödinger's cat thought experiment, it also raises difficult questions about the nature of reality. If every possible outcome occurs in some branch of the multiverse, what does that imply about free will, determinism, and the nature of existence? Moreover, the many worlds interpretation challenges our understanding of probability, as it suggests that all possible outcomes are equally real, existing simultaneously in different universes. Despite the theoretical appeal of the multiverse, one of the biggest challenges is the lack of direct empirical evidence. By definition, other universes in a multiverse would be beyond our observable horizon, making them inaccessible to direct observation. This has led some critics to argue that the multiverse is not a scientific hypothesis, but rather a philosophical or metaphysical one, since it cannot be tested or falsified by experiment. However, proponents of the multiverse argue that certain indirect evidence might be found, such as imprints on the cosmic microwave background, CMB, from collisions between our bubble universe and others, or specific signatures in the distribution of galaxies that could suggest the influence of other universes. Recent advances in observational cosmology have provided some tantalizing hints that could be consistent with a multiverse. For example, the Planck satellite, which mapped the CMB with unprecedented precision, found certain anomalies in the data that some researchers speculate might be evidence of interactions with other bubble universes. However, these anomalies could also be explained by more mundane astrophysical processes, and further investigation is needed to determine whether they indeed point to the existence of a multiverse. The implications of the multiverse extend beyond theoretical physics and cosmology, challenging our deepest assumptions about reality, causality, and the nature of existence itself. If the multiverse exists, it suggests that reality is far more complex and diverse than we ever imagined, with countless other worlds existing alongside our own, each with its own unique history and future. This idea forces us to reconsider what it means to exist, to be conscious, and to make choices, as every possible outcome of our decisions might be realized in some other universe. The multiverse also raises profound philosophical and existential questions. If there are indeed an infinite number of universes, each with its own version of reality, what does that imply about our own universe? Are we just one of countless versions of ourselves, each living out different lives in different realities. This idea can be unsettling, as it suggests that our sense of individuality and uniqueness might be an illusion. Moreover, the concept of an infinite multiverse challenges the principle of Occam's razor, which states that the simplest explanation is usually the correct one. Some argue that the multiverse is an unnecessary complication, introduced to explain phenomena that might be accounted for by other, simpler theories. Nevertheless, the multiverse hypothesis has significant implications for our understanding of the universe and our place within it. If the multiverse exists, it would provide a natural explanation for the fine-tuning of the physical constants in our universe, values that seem remarkably well-suited for the existence of life. In a multiverse, where all possible values of these constants are realized in different universes, it is not surprising that we find ourselves in a universe where the conditions are just right for life to develop. This anthropic reasoning, while controversial, offers a potential solution to the problem of fine-tuning without invoking supernatural explanations. In addition to its implications for cosmology and philosophy, the multiverse also has potential implications for the future of science and technology. For example, if the multiverse exists, it could offer new possibilities for quantum computing, as parallel universes could be harnessed to perform complex calculations simultaneously. This could revolutionize fields such as cryptography, artificial intelligence, and materials science, leading to breakthroughs that are currently beyond our imagination. Moreover, the multiverse could offer new avenues for exploration, as scientists develop new methods and technologies to probe the boundaries of our universe and search for evidence of other universes. Despite the potential benefits, the study of the multiverse is still in its infancy, and many questions remain unanswered. For example, if the multiverse exists, how many universes are there, and what are their properties? How do these universes interact with each other, if at all? And what are the implications of these interactions for our own universe? These questions are not only of interest to physicists, but also to philosophers, theologians, and anyone seeking to understand the deeper meaning of existence. In conclusion, the concept of the multiverse represents one of the most intriguing and controversial ideas in modern physics and cosmology. It challenges our understanding of reality, forces us to reconsider the nature of existence, and raises profound philosophical and existential questions. While the multiverse remains a speculative hypothesis, it offers a potential explanation for some of the deepest mysteries in cosmology, such as the fine-tuning of the physical constants and the nature of quantum mechanics. As scientists continue to explore the boundaries of our universe and develop new methods for probing the multiverse, we may one day uncover evidence that confirms or refutes this idea, leading to a deeper understanding of the universe and our place within it. As we continue to ponder the mysteries of the multiverse, we are reminded of the many other unknowns in the universe, such as the nature of dark matter and dark energy, which together make up the majority of the universe's mass energy content, yet remain largely unexplained. The study of the multiverse, like the study of dark matter and dark energy, pushes the boundaries of our knowledge and invites us to explore the unknown, seeking answers to the deepest questions about the universe and our place within it. The mysterious nature of dark matter has been one of the most compelling and elusive puzzles in modern astrophysics and cosmology. Although it does not emit, absorb, or reflect light, dark matter exerts a gravitational influence that is essential for the formation and structure of the universe. First hypothesized to account for discrepancies between the observable mass of galaxies and the gravitational forces at play, dark matter is now believed to make up about 27% of the universe's total mass energy content. Yet, despite its pervasive presence, scientists have yet to detect dark matter directly or fully understand its properties. The search for dark matter not only seeks to uncover the fundamental composition of the cosmos, but also promises to illuminate the hidden forces that shape the universe. The concept of dark matter originated in the 1930s when Swiss astronomer Fritz Zwicky observed the motion of galaxies in the Coma cluster. Zwicky noted that the galaxies were moving much faster than could be explained by the visible mass alone. According to the laws of gravity, the galaxies should have been flung apart, if only the visible matter were present. To account for this discrepancy, Zwicky proposed the existence of dark matter, an unseen substance that provides the necessary gravitational pull to keep the galaxies bound together. Although his idea was initially met with skepticism, subsequent observations of other galaxies and galaxy clusters revealed similar anomalies, lending support to the notion that a substantial portion of the universe's mass was invisible. In the 1970s, the study of galaxy rotation curves provided further evidence for dark matter. Astronomer Vera Rubin and her colleague Kent Ford measured the rotation speeds of stars in the outer regions of spiral galaxies and found that these stars were orbiting at nearly constant speeds rather than slowing down as expected based on the distribution of visible matter. This flat rotation curve suggested that there was additional mass present in the galaxies, extending far beyond the visible disk. The presence of dark matter provided a natural explanation for these observations, as it could account for the additional gravitational force required to maintain the observed rotation speeds. Dark matter is not composed of the same particles that make up ordinary matter, such as protons, neutrons, and electrons. Instead, it is thought to consist of new, undiscovered particles that interact with ordinary matter only through gravity and, possibly, weak nuclear forces. Among the leading candidates for dark matter particles are weakly interacting massive particles, WIMPs, and axions. WIMPs are hypothetical particles that are thought to be stable, electrically neutral, and massive enough to account for the observed gravitational effects of dark matter. Axions, on the other hand, are lighter particles that were originally proposed to resolve certain theoretical issues in quantum chromodynamics, the theory that describes the strong nuclear force. Both WIMPs and axions are predicted by various extensions of the standard model of particle physics, making them prime targets for experimental searches. Detecting dark matter directly has proven to be an immense challenge due to its weak interactions with ordinary matter. Numerous experiments around the world are dedicated to the search for dark matter particles, using a variety of techniques. One common approach is to use underground detectors, shielded from cosmic rays and other sources of background radiation, to look for rare interactions between dark matter particles and atomic nuclei. Experiments such as the Large Underground Xenon (LUX) experiment and its successor, LUX Zeppelin, have set some of the most stringent limits on the properties of WIMPs by searching for the faint signals that would result from WIMPs scattering off xenon atoms. Another approach to detecting dark matter involves the use of particle accelerators, such as the Large Hadron Collider (LHC) at CERN. By colliding protons at extremely high energies, the LHC can create conditions similar to those that existed just after the Big Bang, potentially producing dark matter particles that could be detected through their missing energy signatures. While the LHC has yet to find direct evidence for dark matter, it continues to probe new regions of parameter space, providing valuable constraints on theoretical models. In addition to direct detection experiments, scientists are also searching for indirect signals of dark matter by observing the cosmos. If dark matter particles can annihilate or decay into ordinary particles, these processes could produce gamma rays, neutrinos, or other high-energy particles that could be detected by telescopes. The Fermi Gamma Ray Space Telescope, for example, has conducted extensive searches for gamma rays that might result from dark matter annihilations in the center of the Milky Way, where dark matter is expected to be densest. While these searches have not yet yielded definitive evidence for dark matter, they have placed important constraints on the properties of potential dark matter particles. The distribution of dark matter on cosmic scales has also been studied through gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. When light from a distant object, such as a galaxy or a quasar, passes near a massive object like a galaxy cluster, the gravity of the massive object can bend the light, creating multiple images or distorted shapes of the background object. By analyzing these lensing effects, astronomers can map the distribution of dark matter in galaxy clusters and other structures. These studies have revealed that dark matter is not uniformly distributed, but instead forms clumps and filaments that trace the large-scale structure of the universe. Despite the extensive evidence for dark matter from astrophysical and cosmological observations, the lack of direct detection has led some scientists to explore alternative explanations. One such alternative is modified Newtonian dynamics, NMON, a theory that proposes a modification of Newton's laws of motion to account for the observed behavior of galaxies without invoking dark matter. While MOND can explain certain aspects of galaxy rotation curves, it struggles to account for the full range of astrophysical and cosmological phenomena, such as the cosmic microwave background radiation and the large-scale structure of the universe, that are well explained by dark matter. The search for dark matter is one of the most active and exciting areas of research in physics, with new experiments and observations continuously pushing the boundaries of our understanding. As scientists refine their techniques and develop new methods, the prospect of discovering dark matter particles becomes increasingly plausible. The detection of dark matter would not only solve one of the greatest mysteries in cosmology, but also open up new avenues for research into the fundamental nature of the universe. The implications of discovering dark matter extend far beyond the realm of physics. Understanding the true nature of dark matter would provide insights into the formation and evolution of galaxies, the dynamics of galaxy clusters, and the overall structure of the universe. It would also have profound implications for our understanding of the fundamental forces and particles that govern the universe, potentially leading to a new era of physics that goes beyond the standard model. Moreover, the study of dark matter has the potential to inform our search for other elusive phenomena, such as dark energy, which is thought to be driving the accelerated expansion of the universe. While dark matter and dark energy are distinct concepts, both represent gaps in our current understanding of the universe's composition and behavior. Solving the mystery of dark matter could provide clues that help us unravel the equally enigmatic nature of dark energy, bringing us closer to a complete and unified picture of the cosmos. In conclusion, dark matter remains one of the most profound and enduring mysteries in science, shaping our understanding of the universe while eluding direct detection. The evidence for dark matter is compelling, from the rotation curves of galaxies to the large-scale structure of the cosmos. Yet its true nature remains unknown. The search for dark matter continues to drive innovation in experimental physics, astrophysics, and cosmology, with the potential to revolutionize our understanding of the universe. As scientists continue to explore the invisible side of the cosmos, the discovery of dark matter could mark a watershed moment in the history of science, revealing the hidden structure of the universe and deepening our knowledge of the fundamental forces that govern it. As we consider the implications of dark matter for our understanding of the universe, we are reminded that there are many other mysteries awaiting discovery. Just as the search for dark matter has opened up new avenues of research, so too does the ongoing investigation of dark energy, the multiverse, and the nature of space-time itself. Each of these mysteries challenges our understanding of the cosmos and drives us to explore the unknown, seeking answers to the deepest questions about the universe and our place within it. The future of space exploration is poised to take humanity farther than ever before, venturing beyond the confines of our home planet to explore new worlds, distant moons, and the mysteries of the cosmos. Central to this ambitious endeavor is the concept of interstellar travel, journeys that extend beyond our solar system to the stars and planets orbiting distant suns. While interstellar travel has long been a staple of science fiction, transforming it into reality presents one of the most significant challenges in the history of human exploration. The vast distances between stars, the limitations of current propulsion technologies, and the need for life-sustaining systems capable of functioning for decades or even centuries make interstellar travel an endeavor that will require unprecedented innovation and international collaboration. The nearest star system to our own, Alpha Centauri, is located approximately 4.37 light-years away. While this distance is minuscule on the cosmic scale, it poses a colossal challenge for space travel. A light-year, the distance that light travels in 1 year, is about 5.88 trillion miles, 9.46 trillion kilometers. To put this in perspective, the fastest spacecraft ever built, NASA's Parker Solar Probe, travels at speeds of up to 430,000 miles per hour, 700,000 kilometers per hour. Even at this incredible speed, it would take over 17,000 years to reach Alpha Centauri. Clearly, if humanity is to venture beyond the solar system, we must develop new propulsion systems that can achieve a significant fraction of the speed of light, along with strategies for sustaining human life over long-duration missions. One of the most promising concepts for achieving the high speeds necessary for interstellar travel is the use of light sails powered by lasers. This idea, often referred to as a laser sail, involves a spacecraft equipped with a large, thin sail that captures the momentum of photons, particles of light, beamed from a powerful laser array based on Earth or in orbit. The concept was popularized by physicist and science fiction author Robert Forward in the 1980s and has since gained serious consideration within the scientific community. The Breakthrough Starshot Initiative, announced in 2016 by billionaire Yuri Milner and supported by physicist Stephen Hawking, aims to develop such a system to send small, lightweight probes to Alpha Centauri at speeds of up to 20% of the speed of light. At this speed, the journey to Alpha Centauri would take about 20 years, making it feasible to explore our nearest stellar neighbor within a single generation. The technology required to build and deploy a laser sail is still in its infancy, but progress is being made. The proposed Breakthrough Starshot mission envisions using a ground-based or orbital laser array to generate a beam of light with a power output of about 100 gigawatts, enough to accelerate a gram-scale spacecraft equipped with a sail a few meters in diameter to relativistic speeds. The challenge lies in developing a sail material that is both extremely lightweight and capable of withstanding the intense forces and heat generated by the laser. Additionally, the mission would require precise targeting and guidance to ensure that the sail remains aligned with the laser beam over vast distances and that the probe can navigate to its destination and relay data back to Earth. In parallel with the development of light sails, researchers are also exploring other advanced propulsion technologies that could enable interstellar travel. One such technology is nuclear fusion propulsion, which has the potential to provide the high energy density needed for long-duration space missions. Fusion, the process that powers the sun, involves fusing atomic nuclei together to release vast amounts of energy. A spacecraft powered by a fusion engine could, in theory, reach speeds much higher than those achievable with current chemical rockets. The challenge, however, lies in achieving controlled fusion in a space environment, as well as managing the heat and radiation generated by the process. Several concepts for fusion propulsion are being studied, including the direct fusion drive, DFD, developed by Princeton Satellite Systems, which uses a fusion reactor to heat and expel plasma, generating thrust. Another promising concept is antimatter propulsion, which leverages the annihilation of matter and antimatter to produce energy. When a particle of antimatter meets its corresponding particle of matter, they annihilate each other, converting their mass into energy according to Einstein's equation E = mc2 EnC2. This process is incredibly efficient, with a tiny amount of antimatter capable of producing immense amounts of energy. An antimatter-powered spacecraft could potentially achieve speeds close to that of light, making interstellar travel more feasible. However, producing, storing, and controlling antimatter in sufficient quantities remains a significant technological challenge. Currently, antimatter is produced in only minuscule amounts in particle accelerators, and it is extraordinarily expensive to create and store. While these advanced propulsion concepts hold promise, they also highlight the broader challenges of interstellar travel, particularly the need for life support systems capable of sustaining human crews over extended periods. Even if a spacecraft could travel at a significant fraction of the speed of light, a journey to the nearest stars would still take years or decades. During this time, the spacecraft would need to provide food, water, air, and waste management for the crew, as well as protection from cosmic radiation and the psychological effects of prolonged isolation in deep space. To address these challenges, Researchers are exploring concepts such as artificial gravity, which could be generated by rotating the spacecraft to simulate the effects of gravity and prevent the detrimental health effects of long-term weightlessness. Additionally, advances in biotechnology, such as the development of closed-loop life support systems that recycle air, water, and nutrients, could be critical for sustaining life on long-duration missions. These systems would need to be highly reliable and capable of functioning autonomously, as resupply from Earth would be impossible. The possibility of cryogenic sleep or suspended animation is another area of active research that could play a role in interstellar travel. If astronauts could be placed in a state of deep hibernation, their metabolic needs would be drastically reduced, minimizing the resources required for the journey. While cryogenic sleep is a staple of science fiction, recent advances in medical science, such as therapeutic hypothermia and the study of hibernating animals, suggest that it may one day be feasible to induce and safely maintain a state of hibernation in humans. Interstellar travel also presents significant challenges in terms of communication and navigation. The vast distances involved mean that communication with Earth would experience delays of years, requiring spacecraft to operate with a high degree of autonomy, navigating across interstellar space, where gravitational influences are minimal and the spacecraft must travel for years without course corrections, would also require highly precise instruments and robust systems for detecting and avoiding hazards such as interstellar dust and debris. Despite these challenges, the pursuit of interstellar travel has profound implications for our understanding of the universe and our place within it. The discovery of exoplanets, planets orbiting stars beyond our solar system, has fueled the imagination and sparked new interest in the search for life beyond Earth. With over 4,000 confirmed exoplanets discovered so far, including some that reside in the habitable zone, where conditions might be right for liquid water and life, the potential for finding another Earth-like world has never been greater. Interstellar probes or missions could provide the first direct observations of these distant worlds, offering insights into their atmospheres, climates, and potential for supporting life. Moreover, the technological advancements required for interstellar travel could have far-reaching benefits for space exploration and other fields. The development of advanced propulsion systems, life support technologies, and autonomous systems could enhance our ability to explore and settle other parts of the solar system, such as Mars, the moons of Jupiter and Saturn, and the asteroid belt. These technologies could also drive innovations in energy production, materials science, and medicine, with potential applications here on Earth. Interstellar travel represents the next great leap in humanity's exploration of the cosmos, challenging us to push the boundaries of our technological capabilities and expand our horizons beyond the solar system. While the challenges are formidable, the potential rewards are immense, offering new opportunities for discovery, innovation, and the potential to answer some of the most profound questions about our place in the universe. As we continue to develop the technologies and strategies needed to make interstellar travel a reality, we move closer to a future where humanity can explore the stars, seeking out new worlds and new possibilities for life beyond Earth. As we look to the future of space exploration, the quest for interstellar travel serves as a reminder of the boundless potential of human ingenuity and the enduring drive to explore the unknown. This journey will undoubtedly inspire new generations of scientists, engineers, and explorers to take up the challenge, pushing the limits of what is possible and leading humanity into a new era of discovery. The exploration of the cosmos is not just a scientific endeavor, it is a testament to our shared curiosity, creativity, and determination to understand the universe and our place within it. Quantum mechanics, one of the most successful theories in the history of science, describes the behavior of particles at the smallest scales of energy levels of atoms and subatomic particles. However, it also introduces some of the most puzzling and counterintuitive concepts in physics. Among these is the phenomenon known as quantum entanglement, a process where two or more particles become linked in such a way that the state of one particle instantly influences the state of another, regardless of the distance between them. Albert Einstein famously referred to this phenomenon as spooky action at a distance. a phrase that reflects both the strange nature of entanglement and Einstein's skepticism about its implications. Yet, quantum entanglement is not just a theoretical curiosity. It has been experimentally confirmed and is now a cornerstone of quantum information science, with profound implications for our understanding of reality and the future of technology. At the heart of quantum entanglement is the principle of superposition, a fundamental concept in quantum mechanics. Superposition states that particles, such as electrons or photons, can exist in multiple states simultaneously until they are measured. For example, an electron in a superposition can be in a state of both spin-up and spin-down at the same time. When a measurement is made, the superposition collapses to a single state. But before this collapse, the particle's state is not definite. It is a mixture of all possible states. Quantum entanglement occurs when two particles are prepared in such a way that their quantum states become intertwined, forming a single, shared quantum system. In this entangled state, the properties of one particle are directly related to the properties of the other, no matter how far apart they are. If one of the entangled particles is measured and found to be in a particular state, the other particle will instantly be found in a corresponding state, even if the two particles are separated by vast distances. This instantaneous correlation between entangled particles defies the classical understanding of causality, where information cannot travel faster than the speed of light, and it challenges our notions of locality, the idea that objects are only directly influenced by their immediate surroundings. The mathematical description of entanglement is elegantly captured by what is known as a quantum state vector, or wave function, that describes the entire system of entangled particles. For two particles, the wave function does not simply describe the state of each particle individually. Instead, it describes the joint state of both particles as a single entity. This means that the measurement outcomes of one particle are inherently connected to the measurement outcomes of the other, a property known as quantum correlation. These correlations are so strong that they cannot be explained by any classical means, a fact that has been confirmed through numerous experiments. One of the most famous experiments demonstrating quantum entanglement is the Bell test experiment, named after physicist John Bell, who in 1964 formulated a theorem that allows for the testing of quantum entanglement against classical theories. Bell's theorem shows that if the world were governed by classical physics, the correlations between measurements on entangled particles would obey certain limits, known as Bell inequalities. However, quantum mechanics predicts correlations that violate these inequalities. Over the decades, a series of increasingly sophisticated Bell test experiments have been performed, most famously in the 1980s by physicist Alain Aspect and his colleagues, confirming the predictions of quantum mechanics and demonstrating that entanglement produces correlations stronger than any classical system could achieve. The implications of quantum entanglement extend far beyond the realm of theoretical physics. One of the most exciting applications of entanglement is in the field of quantum computing, where entangled particles, or qubits, serve as the basic units of information. Unlike classical bits, which can be either 0 or 1, qubits can exist in superpositions of 0 and 1, allowing quantum computers to process vast amounts of information simultaneously. When qubits are entangled, operations performed on one qubit can instantly affect the others, even if they are separated by large distances. This property allows quantum computers to solve certain types of problems much faster than classical computers, offering potential breakthroughs in areas such as cryptography, materials science, and drug discovery. Quantum entanglement also plays a crucial role in quantum teleportation, a process by which the state of a quantum system can be transmitted from one location to another without physically transferring the system itself. In a typical quantum teleportation protocol, two parties, often called Alice and Bob, share a pair of entangled particles. Alice performs a specific type of measurement on her particle and on the particle whose state she wishes to teleport. She then sends the result of her measurement to Bob via a classical communication channel. Using this information, Bob can manipulate his particle to recreate the state of Alice's original particle. while quantum teleportation does not allow for faster-than-light communication. As the classical communication still obeys the speed of light limit EO, it provides a powerful method for transmitting quantum information with perfect fidelity. Quantum entanglement also underpins the security of quantum cryptography, particularly in protocols such as quantum key distribution, QKD. In QKD, entangled particles are used to generate a shared secret key between two parties. Any attempt by an eavesdropper to intercept the key would disturb the entangled state, alerting the communicating parties to the presence of the eavesdropper and ensuring the security of the communication. One of the most well-known QKD protocols is BB84, developed by Charles Bennett and Gilles Brassard in 1984, which has been experimentally realized in various forms, including over long distances through optical fibers and even via satellite communication. The phenomenon of quantum entanglement is not without its challenges and controversies. One of the most famous debates surrounding entanglement involves the EPR paradox, named after a 1935 paper by Einstein, Podolsky, and Rosen. In this paper, the authors argued that quantum mechanics, as described by the wave function, was an incomplete theory because it allowed for the seemingly instantaneous effects of entanglement, which they believed contradicted the principle of locality. They suggested that there might be hidden variables that determined the outcomes of quantum measurements, preserving classical causality and locality. However, Bell's theorem and subsequent experiments have shown that no local hidden variable theory can reproduce the predictions of quantum mechanics, leading to the acceptance of entanglement as a genuine quantum phenomenon. Despite its strange and counterintuitive nature, quantum entanglement has become a cornerstone of modern quantum theory and technology. Its potential applications in quantum computing, quantum communication, and quantum cryptography could revolutionize the way we process and transmit information, with far-reaching implications for technology, security, and our understanding of the universe. However, the full implications of quantum entanglement for our understanding of reality are still not entirely understood. For instance, entanglement raises profound questions about the nature of information, the structure of space and time, and the limits of human knowledge. Some physicists have proposed that entanglement could be connected to the geometry of space-time itself, suggesting that the fabric of the universe might be woven from entangled quantum states. Others have speculated that entanglement could play a role in the resolution of some of the deepest puzzles in theoretical physics, such as the black hole information paradox or the unification of quantum mechanics with general relativity. The exploration of quantum entanglement is also pushing the boundaries of experimental physics. Researchers are developing new ways to create, manipulate, and measure entangled states with increasing precision and over greater distances. For example, in 2017, Chinese scientists successfully demonstrated quantum entanglement and teleportation over a record-breaking distance of more than 1,200 kilometers using the Messier satellite. This experiment not only confirmed the robustness of entanglement, but also opened up the possibility of a global quantum communication network, where secure information can be transmitted via entangled particles between ground stations around the world. As our understanding of quantum entanglement deepens, we are likely to uncover even more surprising and powerful applications of this phenomenon. The ongoing research into entanglement is part of a broader effort to explore the quantum nature of the universe, a quest that has already led to remarkable advances in science and technology. The study of entanglement is not just about understanding the behavior of particles at the quantum level. It is about exploring the fundamental principles that govern reality itself, and potentially discovering new ways to harness the power of the quantum world for the benefit of humanity. In conclusion, quantum entanglement is one of the most intriguing and mysterious phenomena in modern physics, with profound implications for our understanding of the universe and the development of new technologies. It challenges our classical intuitions about the nature of reality, introducing concepts that seem almost magical in their strangeness. Yet entanglement is also a well-established and experimentally verified aspect of quantum mechanics, with applications that could revolutionize computing, communication, and cryptography. As scientists continue to explore the mysteries of entanglement, they are likely to uncover new insights that will deepen our understanding of the quantum world and open up new frontiers in science and technology. This journey into the heart of quantum mechanics promises to reveal the hidden connections that bind the universe together, offering a glimpse into the fundamental structure of reality itself. The cosmos is a realm of immense scale and complexity, filled with phenomena that challenge our understanding of physics and push the boundaries of human knowledge. Among the most awe-inspiring and enigmatic objects in the universe are black holes, regions of space where gravity is so intense that nothing, not even light, can escape. These cosmic behemoths are not merely objects of fascination. They are central to many of the most pressing questions in astrophysics and cosmology. Black holes are thought to be the engines driving some of the most energetic processes in the universe, from quasars to gamma-ray bursts, and they play a crucial role in the evolution of galaxies. Yet, despite decades of study, black holes remain shrouded in mystery, challenging our understanding of space, time, and the fundamental laws of nature. A black hole is formed when a massive star exhausts its nuclear fuel and collapses under the force of its own gravity. If the core of the star is sufficiently massive, typically more than 3 times the mass of the Sun, no known force can stop the collapse, and the core continues to compress until it forms a singularity, a point of infinite density where the laws of physics as we know them break down. Surrounding the singularity is the event horizon, the boundary beyond which nothing can escape the black hole's gravitational pull. The size of the event horizon is proportional to the mass of the black hole, with the radius of the event horizon known as the Schwarzschild radius. For a black hole with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. The concept of black holes dates back to the 18th century, when the English philosopher and scientist John Michel and the French mathematician Pierre-Simon Laplace speculated about the existence of dark stars, whose gravity would be so strong that not even light could escape. However, the modern understanding of black holes is rooted in Albert Einstein's theory of general relativity, published in 1915. General relativity describes gravity not as a force, but as a curvature of space-time caused by mass and energy. In 1916, the German physicist Karl Schwarzschild derived the first exact solution to Einstein's equations, describing the gravitational field of a spherical non-rotating mass, what we now know as a black hole. For many years, black holes were considered a mathematical curiosity rather than a physical reality. It was not until the 1960s, with the discovery of quasars, extremely luminous objects powered by supermassive black holes at the centers of galaxies, that black holes became an accepted part of astrophysics. Today, astronomers have found compelling evidence for the existence of black holes in a variety of contexts, from stellar mass black holes formed from collapsing stars to supermassive black holes with millions or even billions of times the mass of the Sun, lurking at the centers of most galaxies, including our own Milky Way. One of the key areas of research in black hole physics is the study of accretion disks, structures formed by matter that spirals into a black hole. As gas and dust fall toward the event horizon, they form a rotating disk that heats up due to friction and gravitational forces, emitting enormous amounts of radiation, particularly in the X-ray part of the spectrum. The process of accretion can convert up to 40% of the rest mass of the infalling matter into radiation, making black hole accretion disks among the most efficient energy sources in the universe. Observations of these disks, using X-ray telescopes such as NASA's Chandra X-ray Observatory and ESA's XMM Newton, provide valuable insights into the behavior of matter in extreme gravitational fields and offer indirect evidence of the presence of black holes. Another significant development in the study of black holes came in 2015, with the first direct detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, LIGO. Gravitational waves are ripples in space-time produced by the acceleration of massive objects, such as the collision and merger of black holes. The waves detected by LIGO were produced by the merger of 2 stellar mass black holes. each about 30 times the mass of the Sun, located more than 1 billion light-years from Earth. This groundbreaking discovery confirmed a key prediction of general relativity and opened a new window for observing the universe, allowing astronomers to study black holes and other exotic objects in ways that were previously impossible. One of the most challenging aspects of black hole physics is understanding the nature of the singularity at the center of a black hole. According to general relativity, the singularity is a point where the curvature of space-time becomes infinite, and the known laws of physics no longer apply. This raises fundamental questions about the nature of space, time, and matter under such extreme conditions. Some physicists believe that a complete theory of quantum gravity, a theory that would unify general relativity with quantum mechanics, will be necessary to fully understand the nature of singularities and resolve the apparent paradoxes they present. The study of black holes also intersects with the concept of information paradox, one of the most intriguing problems in theoretical physics. According to quantum mechanics, information about the state of a physical system should never be lost. However, when matter falls into a black hole, it appears that the information contained in that matter is lost to the universe when the black hole eventually evaporates through a process known as Hawking radiation. This radiation, named after physicist Stephen Hawking, who proposed it in 1974, suggests that black holes can slowly lose mass and energy, eventually disappearing altogether. The apparent loss of information in this process seems to violate the principles of quantum mechanics, leading to what is known as the black hole information paradox. Resolving this paradox remains one of the most important open questions in the quest to understand the fundamental nature of the universe. Recent advancements in black hole research have also been driven by the Event Horizon Telescope, EHT, an international collaboration that links radio telescopes around the world to create an Earth-sized interferometer. In 2019, the EHT collaboration released the first ever image of a black hole's event horizon, specifically the supermassive black hole at the center of the galaxy M87, located about 55 million light-years from Earth. This image, showing a bright ring of light surrounding a dark shadow, provided direct visual evidence of the existence of a black hole and offered new insights into the behavior of matter and energy near the event horizon. The success of the EHT has paved the way for future observations that could help test the predictions of general relativity in the strong field regime and further our understanding of black holes. Black holes also play a crucial role in the evolution of galaxies. Observations suggest that the mass of a galaxy's central supermassive black hole is closely correlated with the mass of the galaxy's bulge, a relationship known as the M-sigma relation. This correlation hints at a deep connection between the growth of black holes and the formation of galaxies. The energy released by accretion onto supermassive black holes, in the form of jets and radiation, can influence star formation in the host galaxy, a process known as feedback. Feedback mechanisms are thought to regulate the growth of galaxies and play a key role in shaping the large-scale structure of the universe. The implications of black hole research extend beyond astrophysics, offering potential insights into the fundamental nature of reality. For example, the study of black holes has inspired new ideas in the field of holography, particularly the holographic principle law, which suggests that all the information contained in a volume of space can be encoded on the boundary of that space, much like a hologram. This idea, originally proposed by physicists Gerard T. Hooft and Leonard Susskind, has led to the development of the ADAS-CFT correspondence, a powerful theoretical tool that has provided insights into both quantum gravity and strongly interacting quantum systems. In addition to their scientific significance, black holes have captured the public imagination, becoming symbols of the unknown and the mysterious in the cosmos. Their portrayal in popular culture, from science fiction novels to movies like Interstellar, has helped bring the fascinating and complex world of astrophysics to a broader audience, sparking curiosity and inspiring future generations of scientists. In conclusion, black holes represent some of the most fascinating and mysterious objects in the universe, challenging our understanding of physics and pushing the limits of scientific exploration. From their role in the evolution of galaxies to their connection with fundamental questions about space, time, and information, black holes continue to be at the forefront of astrophysical research. Recent advancements, such as the detection of gravitational waves and the imaging of a black hole's event horizon, have provided new tools for studying these enigmatic objects and have opened up new avenues for future discoveries. As we continue to explore the mysteries of black holes, we are likely to uncover new insights that will deepen our understanding of the universe and its underlying laws, driving us ever closer to a more complete picture of the cosmos and our place within it. As we delve further into the mysteries of black holes, we are inevitably led to consider the broader implications of their existence for our understanding of the universe, including questions about the nature of spacetime, the unification of quantum mechanics and general relativity, and the ultimate fate of the cosmos. These questions will continue to challenge and inspire scientists as they seek to unlock the secrets of the universe's most extreme environments. The concept of cosmic inflation is one of the most significant advancements in our understanding of the early universe. Proposed in the early 1980s by physicist Alan Guth, cosmic inflation refers to a brief period of extremely rapid expansion that occurred fractions of a second after the Big Bang. This theory was introduced to address several perplexing issues with the traditional Big Bang model, such as the horizon problem, the flatness problem, and the absence of magnetic monopoles. Inflation theory posits that during this incredibly short interval, the universe expanded exponentially, smoothing out any initial irregularities and setting the stage for the large-scale structure we observe today. Since its inception, the theory of inflation has become a cornerstone of modern cosmology, profoundly influencing our understanding of the universe's origins and its subsequent evolution. At its core, cosmic inflation addresses the horizon problem, which arises from the observation that distant regions of the universe have nearly identical temperatures despite being separated by vast distances that would prevent them from ever being in causal contact under the standard Big Bang model. According to inflationary theory, before the inflationary period, the universe was much smaller and more homogeneous, allowing distant regions to come into thermal equilibrium. When inflation occurred, these regions were rapidly stretched apart, explaining the observed uniformity in the cosmic microwave background, CMB radiation, the afterglow of the Big Bang. Another key issue that inflation resolves is the flatness problem, which relates to the observed flatness of the universe on large scales. The standard Big Bang model predicts that any slight curvature in the early universe would become more pronounced over time, leading to a highly curved universe today. However, observations indicate that the universe is remarkably flat. Inflation explains this by proposing that the rapid expansion flattened out any initial curvature, much like the surface of a balloon appears flatter as it inflates. This flattening effect means that the universe we observe is almost perfectly flat, consistent with measurements of the CMB and the distribution of galaxies. Inflation also provides a solution to the monopole problem, a theoretical issue in particle physics. Certain grand unified theories, GUTs, predict the existence of magnetic monopoles, hypothetical particles that carry a single magnetic charge. If these monopoles were produced in the early universe, they should be abundant today, yet none have been observed. Inflationary theory suggests that any monopoles created before inflation would have been diluted to an undetectably low density by the rapid expansion, explaining their apparent absence in the universe. The idea of cosmic inflation is not just a theoretical construct. It has been supported by a wealth of observational evidence. One of the most compelling pieces of evidence comes from the study of the CMB, which provides a snapshot of the universe when it was just 380,000 years old. The tiny fluctuations in temperature observed in the CMB are believed to be the imprints of quantum fluctuations that were stretched to macroscopic scales during inflation. These fluctuations seeded the formation of galaxies and large-scale structures in the universe. Observations of the CMB by satellites such as NASA's Cosmic Background Explorer, COBA, the Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck mission have provided detailed maps of these temperature fluctuations, which match the predictions made by inflationary models. Recent developments in observational cosmology have further tested the predictions of inflation. One of the most anticipated discoveries would be the detection of primordial gravitational waves, ripples in space-time produced by the rapid acceleration of mass during inflation. These waves would leave a distinct signature in the polarization pattern of the CMB, known as B-mode polarization. In 2014, the BICEP-2 experiment at the South Pole initially claimed to have detected such a signal, but subsequent analysis revealed that the observed signal could be attributed to interstellar dust rather than primordial gravitational waves. Despite this setback, the search for these waves continues, with experiments like the BICEP-3, the Keck array, and the future CMB-S4 project aiming to detect this elusive signal and provide direct evidence for inflation. While inflationary theory has been remarkably successful in explaining several key features of the universe, it is not without its challenges and open questions. One of the most significant issues is the so-called initial conditions problem. Inflation explains how the universe evolved after inflation began, but it does not explain what caused inflation to start in the first place. The conditions that would trigger inflation are still a subject of intense research and debate. Some theories suggest that inflation could arise naturally from the quantum fluctuations of a scalar field, known as the inflaton, but the exact nature of this field remains unknown. Another area of active research is the multiverse implication of inflation. Some versions of inflationary theory suggest that inflation may not have been a one-time event, but could be an ongoing process, leading to the creation of multiple bubble universes within a larger multiverse. Each bubble universe could have different physical properties and constants, potentially leading to a vast and diverse array of universes with different laws of physics. This idea, while speculative, has profound implications for our understanding of the universe and raises deep philosophical questions about the nature of reality and our place within it. The ongoing exploration of inflationary theory also intersects with the search for a deeper understanding of the fundamental forces of nature. Inflation is often associated with high-energy physics, particularly the theories that seek to unify the forces of nature, such as string theory and grand unified theories. These theories predict that during the early moments of the universe, the forces we observe today, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were once unified into a single force. As the universe cooled, this symmetry was broken, leading to the separation of these forces and the diverse array of particles and interactions we see today. Inflation could provide a unique window into this high-energy regime, offering clues about the unification of forces and the fundamental structure of space and time. Despite the successes of inflationary theory, some physicists have proposed alternative models to explain the early universe. One such model is the ekpyrotic universe, which posits that the Big Bang was not the beginning of the universe, but rather the result of a collision between two three-dimensional branes in a higher dimensional space. This model offers a different explanation for the observed flatness and homogeneity of the universe, without requiring a period of rapid inflation. However, like inflation, the ekpyrotic model has its own challenges and requires further development and testing. As we continue to explore the implications of inflation, new observations and experiments will play a crucial role in refining our understanding of the early universe. The next generation of CMB experiments, combined with advances in particle physics and high-energy astrophysics, will provide more precise data that could confirm or challenge the predictions of inflationary models. Additionally, the study of large-scale structures in the universe, such as the distribution of galaxies and the properties of dark matter, will offer further insights into the nature of inflation and its role in shaping the cosmos. The exploration of cosmic inflation is not just an academic exercise, it has profound implications for our understanding of the universe and our place within it. By studying the earliest moments of the universe, we are probing the fundamental laws of nature and seeking to answer some of the most profound questions in science. What is the origin of the universe? What are the fundamental forces that govern its behavior? And what is the ultimate fate of the cosmos? In conclusion, the theory of cosmic inflation has revolutionized our understanding of the early universe and provided a powerful framework for explaining many of the key features of the cosmos. While challenges and open questions remain, inflationary theory has been remarkably successful in matching observations and providing insights into the fundamental nature of reality. As we continue to refine our understanding of inflation and explore its implications, we are likely to uncover new and deeper truths about the universe, driving us closer to a comprehensive understanding of the cosmos and its origins. As we delve further into the mysteries of the universe's earliest moments, we are inevitably led to consider the broader implications of these discoveries for our understanding of space, time, and the fundamental forces of nature. These questions will continue to challenge and inspire scientists as they seek to unlock the secrets of the cosmos and explore the vast and mysterious universe that lies beyond our current understanding. The nature of dark energy remains one of the most profound mysteries in cosmology, challenging our understanding of the universe's fundamental structure and evolution. Dark energy is a term used to describe the unknown force or energy that is driving the accelerated expansion of the universe, a phenomenon first observed in the late 1990s. This discovery has profound implications for the fate of the cosmos, suggesting that the universe will continue to expand indefinitely, becoming increasingly cold and empty over time. Despite its significance, dark energy remains poorly understood, with its properties and origins still largely speculative. The quest to unravel the nature of dark energy represents one of the most important scientific challenges of our time, with far-reaching implications for both cosmology and fundamental physics. The concept of dark energy emerged from observations of distant supernovae, which astronomers use as standard candles to measure cosmic distances. In 1998, two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, made a startling discovery. The light from these supernovae was fainter than expected, indicating that they were farther away than predicted by the standard model of cosmology. This implied that the expansion of the universe was not slowing down, as would be expected under the influence of gravity alone, but was instead accelerating. This acceleration suggested the presence of a previously unknown force or energy, now known as dark energy, making up approximately 68% of the total energy content of the universe. The discovery of dark energy fundamentally altered our understanding of the universe. Prior to this discovery, the prevailing view was that the universe's expansion, set in motion by the Big Bang, was gradually slowing due to the gravitational pull of matter. The idea that the expansion could be accelerating was unexpected and required a major revision of cosmological models. To explain this acceleration, cosmologists introduced dark energy into the equations of general relativity, which describes how matter and energy interact with the curvature of spacetime. The simplest explanation for dark energy is the cosmological constant, a term that Albert Einstein originally introduced into his equations to allow for a static universe, but later abandoned after the discovery of cosmic expansion. In this context, the cosmological constant represents a constant energy density filling space homogeneously, exerting a repulsive force that counteracts gravity and drives the acceleration of the universe's expansion. However, the cosmological constant is not the only possible explanation for dark energy. Another leading theory is that dark energy could be a form of dynamic energy field, often referred to as quintessence. Unlike the cosmological constant, which is unchanging over time, quintessence could vary in strength and evolve over the history of the universe. This idea is attractive because it offers a potential explanation for why the effects of dark energy have become dominant only in the relatively recent cosmic past. If dark energy were a dynamic field, it might have been weaker in the early universe, allowing gravity to dominate and slow the expansion before growing stronger and driving the current phase of acceleration. The nature of dark energy is closely linked to the concept of the equation of state, which describes the relationship between the pressure and energy density of dark energy. The equation of state is typically expressed as a parameter WW, where W taditas E1 WW tatu1 corresponds to a cosmological constant. If WW differs from 1,1, it would indicate that dark energy is dynamic, potentially lending support to quintessence or other alternative theories. Current observations, particularly those from the Planck satellite and large-scale galaxy surveys, suggest that WW is very close to 1,1, but with uncertainties that leave room for other possibilities. One of the major challenges in studying dark energy is that it does not interact with matter in any way other than through gravity, making it extremely difficult to detect or measure directly. As a result, cosmologists rely on indirect methods to study its effects on the universe. One of the most important tools for investigating dark energy is the study of large-scale cosmic structures, such as the distribution of galaxies and clusters of galaxies. The way these structures grow and evolve over time is influenced by the competing effects of gravity and dark energy, providing a powerful probe of the properties of dark energy. Observations of the cosmic microwave background, CMB radiation, also provide crucial insights into dark energy. The CMB, the afterglow of the Big Bang, contains imprints of the early universe's conditions and the subsequent evolution of cosmic structures. By comparing the detailed measurements of the CMB with models of the universe's evolution, cosmologists can infer the properties of dark energy and its impact on the expansion rate of the universe. In addition to observational efforts, theoretical physicists are exploring various models that could explain dark energy. One intriguing possibility is that dark energy could be related to modifications of general relativity on cosmological scales. These modified gravity theories propose that the laws of gravity might change at very large distances, leading to the observed acceleration of the universe without requiring the existence of dark energy as a separate entity. Examples of such theories include far gravity and scalar tensor theories, which introduce additional fields or modifications to the curvature of space-time. Another avenue of research is the potential connection between dark energy and quantum field theory, the framework that describes the behavior of fundamental particles and forces. In quantum field theory, empty space, or the vacuum, is not truly empty, but is filled with fluctuating energy fields. Some physicists speculate that dark energy could be related to the vacuum energy of these fields, although the predicted magnitude of this vacuum energy is vastly larger than what is observed as dark energy, leading to the so-called cosmological constant problem. Resolving this discrepancy is one of the major unsolved problems in theoretical physics and could provide crucial insights into the nature of dark energy. As we continue to study dark energy, future observations and experiments will play a critical role in refining our understanding. Several upcoming missions are specifically designed to investigate the properties of dark energy with unprecedented precision. One such mission is the Euclid spacecraft, led by the European Space Agency, ESA, which is set to launch in the coming years. Euclid will map the distribution of galaxies over a large portion of the sky, using techniques such as weak gravitational lensing and galaxy clustering to probe the effects of dark energy on cosmic structure formation. Similarly, NASA's upcoming Nancy Grace Roman Space Telescope, formerly known as WF-1, will survey large areas of the sky in both optical and infrared wavelengths, providing high-resolution data on the expansion history of the universe and the growth of cosmic structures. The Roman Space Telescope will use Type Ia supernovae, baryon acoustic oscillations, and weak lensing to investigate the nature of dark energy, potentially distinguishing between a cosmological constant and dynamic models like quintessence. The study of dark energy has profound implications for our understanding of the universe and its ultimate fate. If dark energy remains dominant and continues to drive the acceleration of the universe's expansion, the cosmos could face a big freeze scenario, where galaxies move increasingly farther apart, and the universe becomes cold and dark as stars burn out and new ones fail to form. Alternatively, if dark energy is dynamic and changes over time, it could lead to more dramatic outcomes, such as a big rip, where the acceleration becomes so extreme that it tears apart galaxies, stars, and even atoms. Understanding the true nature of dark energy is essential for predicting the long-term evolution of the universe and our place within it. In conclusion, dark energy represents one of the most significant and challenging mysteries in modern cosmology. Its discovery has fundamentally altered our understanding of the universe's expansion and raised profound questions about the nature of space, time, and the fundamental forces that govern the cosmos. While much progress has been made in studying dark energy, its true nature remains elusive, and many questions are still unanswered. As we continue to investigate this mysterious force, future observations, theoretical advancements, and technological innovations will be crucial in unraveling the enigma of dark energy and shaping our understanding of the universe's past, present, and future. As we delve deeper into the mysteries of dark energy, we are reminded that the universe is full of unknowns, from the nature of dark matter to the possibility of other dimensions. Each of these mysteries challenges our understanding and drives us to explore further, seeking answers to the fundamental questions that define our existence and our place in the cosmos. The search for extraterrestrial intelligence, SETI, is one of the most intriguing and profound scientific endeavors in human history. It represents our collective effort to answer one of the most fundamental questions: are we alone in the universe? For decades, scientists have been scanning the skies, listening for signals that might indicate the presence of intelligent civilizations beyond Earth. This quest, driven by advances in technology and our expanding understanding of the cosmos, has not only deepened our knowledge of the universe, but also challenged our assumptions about life, intelligence, and our place in the vastness of space. The concept of searching for extraterrestrial life is not new. Philosophers and scientists have speculated about the possibility of life beyond Earth for centuries. However, it was not until the mid-20th century that the search became a scientific pursuit. The advent of radio astronomy provided a new tool for this search, as radio waves can travel vast distances across space with minimal interference. In 1960, astronomer Frank Drake conducted the first modern SETI experiment, known as Project Ozma, using a radio telescope to listen for signals from nearby stars. Although no signals were detected, Project Ozma marked the beginning of SETI as a scientific discipline. At the heart of SETI is the idea that intelligent civilizations, if they exist, might use radio waves or other forms of electromagnetic radiation to communicate across interstellar distances. Radio waves are particularly well suited for this purpose because they can travel through space with little attenuation and can be detected by radio telescopes on Earth. The waterhole region of the radio spectrum, between 1.42 and 1.67 GHz, is of particular interest because it is relatively quiet and free from natural sources of radio noise. This range includes the hydrogen line, a frequency naturally emitted by hydrogen atoms, which is abundant in the universe and might be a universal reference point for intelligent civilizations. One of the key challenges in SETI is distinguishing potential signals from intelligent civilizations from the vast amount of natural radio noise produced by stars, galaxies, and other cosmic phenomena. To address this, SETI researchers look for signals that exhibit characteristics unlikely to be produced by natural sources, such as narrowband signals, those confined to a very small range of frequencies, or signals that show evidence of modulation, indicating an artificial origin. Additionally, SETI projects often focus on stars similar to our Sun, under the assumption that such stars might host planetary systems with conditions conducive to life. Over the years, SETI has evolved from small-scale efforts like Project Ozma to large, coordinated projects involving powerful radio telescopes and sophisticated data analysis techniques. One of the most notable SETI projects is the Breakthrough Listen initiative, launched in 2015 with $100 million in funding from Russian billionaire Yuri Milner. Breakthrough Listen is the most comprehensive and intensive SETI program to date, using some of the world's largest radio telescopes, including the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, to scan the skies for signals from extraterrestrial civilizations. The project aims to survey the 1 million closest stars, the entire plane of the Milky Way, and 100 nearby galaxies over the course of a decade, generating petabytes of data that are analyzed for potential signals of interest. The search for extraterrestrial intelligence is not limited to radio signals. In recent years, researchers have begun to explore other possible means of communication that might be used by advanced civilizations. One such approach is the search for optical SETI, which looks for brief but powerful bursts of light, such as laser pulses, that could be used to transmit information across interstellar distances. Lasers are capable of producing highly directional and intense beams, making them a potential tool for interstellar communication. Optical SETI projects, such as those conducted by the SETI Institute and Harvard University's SETI program, use specialized telescopes to search for these fleeting signals. Another promising avenue for SETI research is the search for technosignatures, indicators of advanced technology that could be detectable from Earth. Technosignatures could take many forms, including large-scale energy usage, such as Dyson spheres, hypothetical structures built around stars to capture their energy output, industrial pollution in planetary atmospheres, or even artificial structures in space. The detection of technosignatures would provide compelling evidence of intelligent life, even in the absence of direct communication signals. NASA and other organizations are increasingly supporting research into technosignatures as part of a broader effort to explore the possibility of life beyond Earth. The discovery of exoplanets, planets orbiting stars outside our solar system, has greatly expanded the scope of SETI. Since the first confirmed exoplanet discovery in 1992, thousands of exoplanets have been identified, many of which reside in their star's habitable zone, where conditions might be right for liquid water and, potentially, life. Missions such as NASA's Kepler and TESS, Transiting Exoplanet Survey satellite, have provided a wealth of data on these distant worlds, allowing scientists to identify targets for SETI searches. The increasing precision of exoplanet detection methods also raises the possibility of characterizing the atmospheres of these planets, searching for biosignatures or signs of technology. Despite decades of searching, SETI has yet to detect a definitive signal from an extraterrestrial civilization. However, this lack of success has not dampened enthusiasm for the search. Instead, it has led to a deeper understanding of the challenges involved and a more refined approach to the search. The vastness of the universe and the limitations of our current technology mean that the search for extraterrestrial intelligence is still in its early stages. The absence of evidence is not evidence of absence, and many researchers believe that the search is worth continuing, given the profound implications of discovering intelligent life beyond Earth. The implications of finding extraterrestrial intelligence would be far-reaching and transformative. It would fundamentally change our understanding of our place in the universe, challenging our assumptions about life, intelligence, and the uniqueness of humanity. Such a discovery would also raise important questions about communication and interaction with other civilizations. How would we respond to a signal from another civilization? What ethical considerations would arise in such a scenario? These questions are the subject of ongoing debate and study within the SETI community and beyond. One of the most intriguing aspects of SETI is the possibility that extraterrestrial civilizations might be vastly different from our own, not only in terms of biology and technology, but also in their methods of communication and even their perception of the universe. Some researchers speculate that advanced civilizations might use communication methods beyond our current understanding or capability to detect. For example, they might communicate using neutrinos, gravitational waves, or quantum entanglement, all of which present significant technical challenges for detection with current technology. Alternatively, they might be using communication strategies that we have yet to conceive, underscoring the importance of keeping an open mind in the search for extraterrestrial intelligence. The search for extraterrestrial intelligence also intersects with other fields of study, such as astrobiology and the study of extremophiles, organisms that thrive in extreme environments on Earth. These fields provide insights into the potential diversity of life forms that might exist in the universe and inform the search for life beyond Earth. For example, the discovery of life in extreme environments, such as deep-sea hydrothermal vents or acidic hot springs, suggests that life could potentially exist in a wide range of environments on other planets or moons, even those that differ significantly from Earth. In addition to its scientific significance, SETI has a profound cultural and philosophical impact. The search for extraterrestrial intelligence taps into some of humanity's deepest questions about existence, purpose, and the nature of life. It connects us to the broader cosmos and invites us to consider our role in a potentially much larger and more complex universe. The search for extraterrestrial intelligence is not just a scientific endeavor. It is a quest to understand our place in the universe and to explore the possibilities of what lies beyond the horizon. In conclusion, the search for extraterrestrial intelligence represents one of the most ambitious and far-reaching scientific endeavors of our time. While the challenges are immense and the outcomes uncertain, the potential rewards are extraordinary. The discovery of intelligent life beyond Earth would be one of the most significant milestones in human history, reshaping our understanding of the universe and our place within it. As technology continues to advance and our understanding of the cosmos deepens, the search for extraterrestrial intelligence will remain a central pursuit in the exploration of the universe. It is a journey that challenges our assumptions, expands our horizons, and connects us to the broader mysteries of existence. As we continue to explore the possibilities of life beyond Earth, the next steps in this journey will involve not only the search for signals, but also the search for evidence of life in the diverse environments of our solar system and beyond. From the icy moons of Jupiter and Saturn to the distant exoplanets orbiting other stars, the quest to find life in the universe is just beginning, with each discovery bringing us closer to answering one of the greatest questions of all. Are we truly alone in the universe?